All right. After a day of significant torture, we continue with something a little bit more relaxed. And there isn't a better performer in this world than Ernesto Lucas, whom I introduced to you, a friend of mine for 20 years. And he's going to talk about what we should think about elliptic genus. Ernesto?
Thank you so much. Well, first I apologize. Especially to the to everyone else too, because my title is still TBA, but now it's not a secret anymore. The subject of this talk was a surprise, even to me, up until very recently. So yesterday evening.
Oh, this is my fault. I apologize, just because I assigned the titles to you and Mohammed.
Yeah. Yesterday evening, I learned that the title of my talk, and so we can have some fun because this subject is very beautiful. But my talk will be very, very light. In fact, I will only give half of the talk because the second talk should be entitled Introduction to Elliptic Cohomologies or TMF or that kind of thing. But I will really not have time for that because I want to very relaxedly explain the origin of all this. Of the elliptic genus, the geometric nature of the elliptic genus, and I may say a word or two how these immediately produce the definition of the elliptic cohomologies and so on and so forth. But let's start by again very relaxedly saying that a genus is something that to a closed oriented manifold associates a complex number. So that if you have the union of two manifolds, you get the addition of the things. The joint union, I should say. The product is the product of the things. And it's the same whenever they are coordinate. This is extremely close to something that will be spoken about in the next talk. But rather than having the cobordism thing, it will be slightly different. But here we have this cobordism thing that is a little bit, well, you do that. So it's already that's a strong conditions. And this is to say that this is a ring homomorphism from oriented cobordism to the complex numbers. But what this second thing means is just what I just spelled out in detail before. It's just that, exactly that. It means cobordism, the ring homomorphism. So you could change this ring a little bit, and then you would have motivic measures, or you could change this ring a little bit, and then you would have some other things. But let's start with that historical thing. We're in the 80s. And so the signature is a very well-known genus related to the intersection form in homology. the A hat genus takes values in, not in the complex numbers, but in half integers, the A hat genus. The Euler number is not a genus, and it is not a cobordism invariant. So this is something that's a little bit confusing because it's modeled on the Euler characteristic, this definition, but the Euler characteristic is not one of these things. Anyway, Tom proved very famous theorem that the cobordism ring, when you kill all the torsion, and this was mentioned on Bernard's talk, it's a polynomial ring on the projective spaces, even dimensional complex projective space. You have this even dimensional complex. And two things were mentioned in Bernard's talk is that these are algebraic manifolds. And that, again, in the next talk, a theorem will appear where the measures of things are kind of some few spaces, you know. It's a little bit like this. We have all it's a little bit model on this story, you know, where we have just the projective space. But we're in the 80s, not in the 2020s. Okay. And it is the same thing, therefore, to have a genus as to have values on projective spaces. The same thing, to have the genus, to have the values on projective spaces. It's just numbers, a lot of numbers. And of course, it's something you do, you just almost instinctively. You write the generating series for the values of the genus. And you call it the log phi of x. That's what you call it. And so it's just a power series. So far it's a formal power series. And so you have a genus, you have one of these, and you have one of these. Well, you have a genus because of Thom's theorem. You need Thom's calculation though. And now, you have this multiplicative property. And yesterday it was asked about bundles and whatnot. Yesterday it was asked, and you asked the question about, to Enrique, I think, about bundles. And it's very important here, because if you have this stronger thing, you have a little bit more than a genus. You know, it's a stronger multiplicative property. And so, A hat satisfies this stronger multiplicative property when F is a spin manifold. And what are all formal power series for which we have this stronger multiplicative property? This stronger multiplicative property, intriguing. King Sao pointed this out yesterday, and we want to classify all the genuses that have this stronger multiplicative property. And it's an incredible theorem, it's striking, that the genuses, the genera for which there are multiplicative for spin manifolds. So you could have it for manifolds. But if you have this stronger multiplicative property for spin manifolds, if and only if it's an elliptic integer. If and only if it's an elliptic integer. It's striking. I mean, how is this even possible? You know? How could you prove something like this? You know, that is so strange. You know? What is it? And this theorem of Okanin is what caused all the further development of the genera. Witten had to give an explanation to this, and he did. And then all the school of TMF, of Hopkins and Ravenel and collaborators, and everything, the source of everything is this theorem. So I wanted to stop in this classical fact from the 1980s for a little while. Well, it's a striking theorem, and whenever I see it, I still cannot quite believe it, you know.
Who proved this theorem again?
Huh?
Who proved the theorem?
Okanin in the 80s.
It's Ushanin.
Oshanin.
I'm sorry, Ushanin.
Oshanin. Sorry about the pronunciation. Anyway, it's a classical thing, amazing thing. And this is really this little thing, this little fact, there's a humble fact, it's really the origin of all the development in elliptic cohomology and a lot of intriguing progress in conformality theory. I could, that would be the third lecture, explaining why conformality theory explains this fact. But I will not do that today. These are the elliptic, they are called elliptic genera because they are elliptic integrals. Of course, you know. They are called elliptic genera. But it is equivalent to say that they are elliptic integrals as to say that they have this intriguing property that intrigued Kyung saw yesterday. So it's the same thing, these two things. And well, you know, universal elliptic genus has these two, we have these two parameters here, and it depends on two parameters, doesn't it? So I could say, what if I think of it as a function of two parameters? Now this thing is a thing, a function of two parameters, and this thing that is a thing is called the universal elliptic genus, because now it's really all of them. So, well, the only part that was proved by Chami, and the part was proved by Clifford Towers. And they use very different techniques, these two proofs. It's very interesting. It's a very interesting story. So we can, of course, the first thing you do when you have this kind of thing, you use you invert the function, the autoelliptic function, and then you have this. All of a sudden, a lattice emerges. That is a period lattice of the elliptic function, of course, and S vanishes at one point omega of order 2 in the elliptic curve, and has a pole at the order 2. And the integral satisfies, it's really, you see, it's about weighted projective space. Well, one of these very small weight, you multiply by lambda squared lambda 4, this thing brings out lambda to the half of the dimension of the manifold. So it has that homogeneity property. And so it's actually a modular form of weight a half of the dimension of the manifold. It's actually a modular form. The universe, again, you see, we already did another weird thing, didn't we? We said, now that we have this function of two variables, and now this function of two variables is a modular form. And it has enormous rigidity properties, as we will see. In fact, the rigidity properties are so strong that they characterize the whole thing and prove the theorem. Because you show that it has these rigidity properties. One side of the thing, the other side of the thing has the rigidity properties, and now there is no options, they are the same thing. It's a slightly strange proof because it's just about the rigidity that you prove that the two things are the same, because they are so constrained. And so you introduce symmetries. This is very much what you would do, again, in some calculations in conformality theory, and that's another clue as to the relevance of CFT in this story. In any case, L is normalized in this way with 2 pi and 4 pi and tau. So you normalize it that way. Now you have this tau thing. And with that normalization, T of m is a holomorphic function. Well, it was a formal power series not a long time ago, and now it is a holomorphic function in tau, the universal one. Modular, and it's a modular form of weight, half the dimension of m, under a subgroup gamma 0, 2. So let me just remind you very quickly what this means. Which presents a half period point omega. A modular form is a complex valued function defined on the upper half plane, and it has three properties. It has you pick a subgroup of a PSL2Z, and then it has this homogeneity property with respect to the action of the subgroup in PSL2Z. It is holomorphic, and it's holomorphic at the cusps too. I mean, it extends holomorphically at the cusps of the thing. So that's a modular form, very important. And but let me just remind you of groups that appear. So you could have the whole thing, or you could have a gamma 0n that are, and I am using gamma 02, but you could have gamma 0n that is just C0 mod n. So I'm having an even thing in the C part of the matrix, And that's the group that we're talking about for this modular form that appears from the genera.
Can I ask one question? When you have said that there is a half dimension M modular form, dimension M is even or?
It has to be even, right? Because, yeah, it is even.
Yeah, otherwise half integer weight modular forms has to come into play from.
That's right, but not today. Today I'm going to do it as simple as possible.
Okay.
So if you feel that a hypothesis is missing, you add it. That's it. But of course it has to be even further. But it's so, and there is these other ones, you know, gamma n, etc. And all of them would play a role if I was doing a careful development of this story. But I'm going to only use gamma 0, 2. Gamma 0, 2. These are typicals. And anyway, nevertheless, it's extremely tempting to mention this one. That is for the full thing. Because at more from a weight 12. And again, today, I will not go much further than this. But this one also plays an important role as in a computation that Bernardo and I, and Thomas Neves and the Fernex did a long time ago that I'll exhibit at the end of the talk. And this one is important, it's weight 12, and it's about the full width. Okay, so those are the classical kind of famous modular forms. And gamma 02 presents the half period point omega. But notice though now that something is absolutely it's obvious, you know, that is this defines the spin structure on the elliptic curve. So it's not about elliptic curves, but elliptic curves with spin structures. And so, and also H gamma 02 is compactified by adding tau equals 0 and tau equals I infinity. And so this is about elliptic curves with a spin structure. And so in terms of, now we do this change of paradigm. And now, observe, just because we're rhyming with the subjects of this conference, and for no other reason, that this is very much in the spirit of the methods that were used by Iritani to prove this law formula and this kind of thing. It's kind of in the same spirit because we're doing this kind of calculation inside cohomology with these kind of formulas, and it's more or less on that same spirit, but there's a kind of a modern revival of this theme from the 80s. Anyway, we're in the 80s, we have the inverse of the universal genus S of U, and this is the formula, and you see the hyperbolic tangent there. And now when you see this formula, you are struck by the fact that it comes from representation theory. So it is the character of a virtual projective unitary representation of the groups of diffeomorphisms of the circle. So you have the group of diffeomorphisms of the circle, you study its representation theory, you study the characters of the representations, and you end up seeing exactly these kinds of formulas also in the 80s. You know, the same formula, and now you are intrigued because you have this representation of the groups of diffeomorphisms of the circle that has the character that is the inverse of the modular, the inverse to the modular form that is the elliptic integral, the universal elliptic integral for the genera for this funny multiplicative formula for bundles gives you all these automatically. Okay, so in fact, if you have the rotation by tau, then you have this representation. You know, it's a visual representation. It has this plus and minus part. It's polarized. And you take this kind of super trace, and the super trace of this representation is exactly this story. You know. But a consequence of this is that you have integral coefficients when expanded in powers of q. And this is non-trivial, but it's true. So they are integral coefficients. So the series is on integral coefficients, which you would expect because it was a genus and so on and so forth of this kind of thing. But it's always integral. You know, the ones that you can write are integral or have integral, and then you suspect this is the. But it's always integral. You cannot do it with non-integral coefficients. Or it descends to the integers always, you know. Well, so you use the tangent bundle, and then you can also think of this as some sort of character, you know. It's a function from K-theory to even cohomology. And this sort of character is something called a stable exponential characteristic class for real vector bundles. It's called, that's what it's called. Let me define what that is. But anyway, this thing is one of those stable exponential characteristic classes for vector bundles. So what is this? Exponential means that, and stable means that for the one-dimensional vector bundle over the point, you don't get zero. You do not get zero. And this is extremely important, stability, and this is what fails for the Euler characteristic. The Euler characteristic is not stable. Well, we know the Euler characteristic is not stable, right? So this is what fails for the Euler characteristic. Well, because stability gives you cobordism invariance. And again, the Euler characteristic is precisely not cobordism invariant. But the way you do the Stokes theorem immediately gives you that stability ensures that this is a cobordism invariant. So any genus can be expressed in terms of a stable exponential characteristic class for real vector bundles. So, and again, notice that we went from cobordism to just KO theory. So we went from our cobordism that is complicated, and this is an extremely important reduction because it allows us to prove the theorem. So we went from cobordism to KO theory by means of the Stokes theorem, and an exponential characteristic class determined by its value on the universal bundle on CP infinity is completely determines an exponential characteristic class, and you have any element there. And so we get another power series associated to phi, that is p phi. This is not log phi, this is p phi of u. And this phi of the universal bundle in this ring. So you take the universal bundle, you compute phi, it's here, so it's a power series, and you have this power series. So it's another power series, but of course going to be related. And so we have that we have the coefficient phi of Pn is just the coefficient of this one, and again it's extremely important that you can invert, that you have stability, and now you can use Lagrange formula for reversion of series. So this is a classical fact from function theory, and now you have this beautiful story, you know. E to the 2 log of this series is u, if and only if u over p of u is x by the Lagrange inversion formula. And this thing, the previous one, that one, is equivalent to this thing. That thing is equivalent to the statement. So we have that is equivalent to this statement, and well, we have a stable exponential characteristic class, lambda phi. And we have the Giese mapping K theory corresponding to the contraction of M to a point. So integration over in K theory over the whole of M. And so we have the topological Riemann-Roch theorem. Given the Chern character, the topological Riemann-Roch theorem tells you that this push forward is precisely the Chern character times the A hat genus of the tangent bundle. That's a universal formula. Is the Riemann-Roch formula. And so we have that chain of that is A inverse times T of E, with phi or power series. And well, for example, we can do the signature, just taking the characteristic class for vector bundles, that is the spin bundle, and we do the signature. Or we can do the other characteristic, but it's unstable. But we can do the other characteristic by this method. Or we can do the universal elliptic genes. So the whole point of this discussion is I give you this characteristic from K-theory. We have this, and we do this spin bundle, and we just do these symmetric bundles and zero powers. We get the elliptic genes. So why did I went through all this argument a little bit too fast to get here? Because typically in algebraic geometry, this is the definition of the elliptic genes. So we get to the definition that you see in the algebraic geometry papers. For example, in the papers of Lipgover and Borisov and etc., you will get this kind of definition. It will look very intriguing at first. Why would you define something like this, like that? But the reason is this calculation that I just did, a little bit too fast. Anyway, it has some advantages, this second definition, and one of them is the Atiyah-Singer index theorem. That thing, the thing that we were doing with the Riemann-Roch theorem is the index of the Dirac operator, because the spinor bundle appeared, and when you have a spin manifold, this is an integer, and then we can prove in this way with this calculation. I went a little bit too fast, but you could go slowly about it. With this calculation, one can prove now, rigorous proof, that this is actually a power series with integer coefficients. It is a classical proof. By the way, I'm following, destroying a little bit various papers of Atiyah and Sigal and Bott, and combining and destroying them a little bit in this classical literature from the 80s.
They won't buy.
Yeah. They do this in far more detail. I'm just giving an impressionistic version of all this classical stuff. Muy bien. So, now, but there is a second advantage. That is now that we can think of the equivariant K-theory, and everything works. So we can introduce, and this is very, very funny story. You know, the proof of the Atiyah-Singer index theorem, the classical proof, the first proof, you needed to do the equivariant version to prove the non-equivariant version. And here is a little bit the same. We do the equivariant. Why would we do the equivariant? Because we can put G all over the place. Okay, we do. But then, by having this equivariant, the ability to do it equivariantly, we can actually prove the integral formula by rigidity. So, because I am using a lot of time, let me just say that we have that for any exponential transformation in theory, it is expressed as a unique polynomial with zero powers, obviously, and therefore it makes perfect sense for a G vector bonds. So it makes perfect sense equivariantly, and the GC map is perfectly well defined. So everything is in the paper by Sigal equivariant K-theory, all these basic foundations of the story. And in the index theorem 2 paper, with any spin, this is a virtual representation of the group. So you have a virtual representation. Now you put a group for no reason. You put a compact group acting on the whole story. And so we have this term, elliptic general characterized by the property that a compact connected group acts on the spin manifold, then P, G of M, is constant as a function of G. So it doesn't depend on G. And so you choose judiciously your G, and then you put G equals to the identity, and you get the non-equivariant thing. from using symmetries using the covariant thing. So it's a very strong rigidity. G may or may not act on the spin bundle, it doesn't matter. And then in the case in which it does not act, you can prove very easily that then this is zero. This constant not only exists, but is zero. Well, now I will not, let me skip to that because I see how time is flowing. But let me say that this integral theorem and this theorem are equivalent. This theorem and the theorem with the integral are exactly the same theorem. And the reason is that you prove that one side is rigid, you prove that the other side is rigid, and now they have to be the same. It's a very peculiar proof. So it's the rigidity of the elliptic genus, and it's equivalent to the integral form. And so, well, I could try to prove that the rigidity implies the formula, or that the formula implies the rigidity, but let me not do it. It's true. So, let me pass to another story that is also extremely important, and that's mathematics. That's mathematics. And now comes mathematical physics, I don't know what to call it. Now comes something that has not been fully mathematized, although big portions of this have been mathematized. But it's Witten's explanation to all these amazing mathematics, you know. You have that this thing is a modular form, and all these things are miraculous and a little bit unmotivated because they depend on the fact that you have this formula. And either one day you wake up and write the formula, or you have no reason to even think that a formula like that could possibly be true. So why would you even think that something like this, even this theory that I described, is even possible? I mean, why would you even think that? But everything up to here is fully proved, and I even give enough details for you to reproduce the whole thing, and it's totally rigorous. But then Witten comes and says, well, wait a second, hold my beer, let's see what's going on. And it says, well, we have its invariance under group action, it's called rigidity. It's a modular form, so it's modularity, rigidity, and it's a representation of the diffeomorphism group of S1. So you have these clues. Historically, Witten had these clues. And then he says, well, this is obvious that what we're seeing, it's a two-dimensional conformal quantum field theory. And even after all these years, one can say that we haven't fully developed the mathematical foundations of this approach that Witten says. But then Witten himself again says, but this is a complicated thing, a little bit, not for a physicist, but it's a theory. You know? Let me write a much smaller theory that captures the same mathematics. Another quantum field theory. That is not this two-dimensional conformality theory, but another simpler theory that is much easier to. And this part has even larger aspects of this part. But this part is very interesting. I couldn't speak about this story, and it's very, very interesting. But we go down and says, but because, yeah, and you can see Witten's writings in this respect, because blah 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 blah. This is the same as the equivariant index of a Dirac operator on loop space. So loop space is an infinite-dimensional manifold, and that's a problem. Because it is an infinite-dimensional manifold, not all of these mathematics have been... There is a famous problem that there is no good measure for some of these integrals, Feynman measure, and all these stories. You know? And nevertheless, Bismuth did manage to produce big parts of what I'm going to say, but not everything. And it is very interesting, the evolution of this. So But in terms of mathematical physics, is the index of the Dirac operator on loop space, and then this would naturally have rigidity, modularity, and would be a representation of diff-S1 because you have this diff-S1 naturally acting on the parameterization of the loops. So you would have all the properties if it was that kind of thing, and we can immediately recognize that all these properties could be explained by a statement of this sort. And here is the computation.
But this also explains why the first proof of Kiesinger was in the equivalent case. Like, is this the reason maybe why they had to go to the equivalent case to prove the non-equivalent?
Well, there is many proofs, of course, at Kiesinger. There is a heat kernel proof that doesn't require that. No, it's a little bit, yeah, because there are little proofs about K-theory. But yeah, I don't have it totally clear in my mind, but yeah, there is a relationship there. Yeah, there is a relationship there, but I don't know. In any case, the operator commutes with the circle action, we rotate the loops, and the index is a virtual representation in Q. And only positive energy characters appear, forming the elliptic genus as a formal power series. A priori, you would not have that, but again, for physical reasons, there is a positive energy condition, and this is reasonable from the point of the mathematical physics of quantum field theory, and indeed, it's compatible with this story. So, well, this is very vague, but I submit you to the paper of Witten to alleviate all these imprecisions. Now, so let's walk a little bit back and let's explain this story from a slightly
Question: is that physics explanation, does it give an explanation for this formula with the elliptic integral too?
Everything, yeah. It explains everything perfectly well, but it's not mathematically rigorous today, after only 40 years or something. So, but in Spanish,
It's clear why we didn't like succeed on explaining these physical theories.
well, I could give the third talk about some of the obvious difficulties and some of the heroic attempts to almost do it. Perhaps the last big attempt was Stoll-Steigner. That was the first last push, and then people were very enthusiastic at the time that finally we're going to do it. And then even then there were problems.
Who was the philosophy?
By Stefan Stolz and Peter Tiger. And Peter Tiger. So that was the last push, but this was already in the 2000s or something.
20 years ago.
Yeah, 20 years ago, something like that. So there have been several revivals trying to understand this. And so the subject is divided into three things. One is the algebraic topologists that with the powerful homotopy theory and algebraic methods prove a lot of these things. And it's a little bit, the proof that I give today of that integral formula is an example of that. It's a proof. It's a very weird proof, you know, but it is a proof of that formula, you know. That is not of the function theory style that one would expect, you know. One would expect a function theory style proof of that formula. Not at all what the algebraic topology can do, but it can do a lot. But then you feel this little lack of, I don't get no satisfaction, you know, with that kind of proof, you know, kind of something is missing or something, you know. And then there is the algebraic geometers that take the formulas and incorporate them in the formalism of algebraic geometry, and even pick up some of the results from the topologists. It's true already, why not, you know? And they do things with that. And in part, we're talking about this in this conference because this third approach but Lev Borisov as well. In that approach, there is this thing that the elliptic genus is a K invariant. You called it something else. You called it
Discrepant.
discrepant
Discrepant relation.
relation thing, whatever. So it's so so there is this at first surprising relation to birational geometry. That is not so surprising from the point of view of conformality theory. From the point of view of conformality theory, because of the R charges and all this story, it's to be expected this kind of behavior for the elliptic genus. So the most powerful conceptual approach is conformality theory, but it is not a mathematical approach. So, and so just the proof that this K thing, it's in the annals of mathematics, for example. You have to do things in algebraic geometry to prove that kind of thing, that it's totally to be expected or proved in the world of conformality theory. So, so this is why I'm talking about this issue today here. It's one of those things that appear in your talk, and in many ways one expects that it is a universal invariant of that sort in the commutative world, but it's already, I think, coming from the non-commutative world. Also, this could be explained. And so it has to be related to the theory of atoms. There is this kind of invariant that is detecting this kind of behavior. These two, and in some cases the calculation of this is exactly equivalent, as Lebowitz proved, to the calculation of the classical spectrum of singularity, in these very simple cases, but of course more global cases where the spectrum doesn't even make sense, you cannot even say that. Nevertheless, Enrique Becerra, Ludmil Katzarkov, and I have a generalized version of the spectrum for which these calculations should still go through in a more generality, and etc. So it's part of this bigger puzzle of what is atom theory about, what does it see, and so on and so forth. And that's why I'm speaking about it today. But anyway, I won't have time to say much more, so I'll go very fast. I'll skip a lot. Let me just give a very impressionistic image of what's next. And then there will be the second talk about how this integral formula would inspire you to produce new cohomology theories, new spectra in homotopy theory, new cohomology theories that would be killing exactly the right amount of torsions in mu, the one that appeared in Bernardo's talk, and MUG and everything, just killing exactly the right pieces in mu gives you the ability to see, and then because you have all these amazing modularity properties and that you can do other things that you cannot do with Kn or with BP, but with mu. So it is very amazing families of spectra are kind of very fine-tuned to do things, but that would be the second talk. And then the third talk maybe would be what is this imaging in conformal theory that would give us at least a considerable heuristic guide to understand what is to be expected in various situations. But let me go all the way back and try to explain how a typical calculation in mathematical physics could go regarding these things, and why such a calculation would give you the K invariance just from the heuristic mathematical physics picture. And then this would have to be transformed into a proof. But we did this calculation a long time ago with the intuition that this could be transformed into a proof. And then we never transformed it into a proof. So it's been there sitting for many years. This proof of the different proof that from the Borisov Lidgover proof, it's a very different proof from the proof, coming from the ideas of the topology and mathematical physics, and the spirit of the proofs that we were talking about today, but we never finished this proof. So I'll just give you an idea that we had, that we wrote a long time ago, and we never kind of followed through, for a proof of this K thing. But a systematization of this idea, a revival and systematization of these ideas could prove to be very useful to clarify some of the many aspects of atom theory. So that's that. Okay, so the Laplacian is that thing, and so we have this theory, this quantum field theory, whose Lagrangian is this Lagrangian. So remember that the Schrödinger equation looks very much like the heat equation, but there is this complex number, that this weak rotation thing, and then the behavior changes very much. But sometimes you can get away with solving a heat equation and then continue with analytic continuation solving the corresponding Schrödinger equation. So you don't see the I is because in that case you can kind of do it like that. In this case you can do it like that. So all the information of the quantum theory is the spectrum of the Laplacian in this thing. And recovering the classical theory from the quantum theory is here in the shape of the drawing. And so the final functional integration approach for the theory allows to compute an integral over the prelude space of the manifold by stationary phase approximation as an integral over L. So the heat kernel, if I wanted a bona fide quantum theory, I would have to add an I here. But I'm weak rotating and cheating and solving a heat equation, not a Schrödinger equation. But anyway, the fundamental solution for the trace of the heat kernels is given by these traces, and this is this finite integral. And so this is the formal part of the Wiener measure. And now we are into this kind of problems that in this particular case, Bismuth solved using elaborate technology from probability theory. And he solved it in a completely rigorous manner using this. And so there is this probabilistic approach to the index theorem that is making rigorous this story. So it turns out that the sum of the trace of the heat kernel is independent of T, a long time limit that is something called the order characteristic by recalling Hodge's theorem using this Hodge decomposition. And the appearance of the Hodge decomposition in all these calculations, it's something that is also one of the reasons why the next talk is the way it is. Why these Hodge decompositions are like Feynman integrals and therefore are this kind of homomorphism from this modified cobordism ring that is going to be introduced in the next talk. And so, and short-time behavior given by an integral complicated curvature expression. And this is the thing, in dimension 2 is not a complicated curvature expression, it's just the Gauss-Bonnet theorem, but this is the Gaussian curvature. But otherwise, it's an elaborate tensor thing. And this is the other characteristic. And now remember that this it's a bad behaved theory. So it's just really a bad behaved theory because we don't have E inverse. We can do the index of the, if you have a spin manifold, you don't take the Laplacian, you take the square root of the Laplacian, now you have the Dirac operator, and now you can recover the index of the Dirac operator. And, but, when we are here, Bernardo and I, and we like orbitals, so we said, why don't we do this story over stacks, of the Montfort stacks? Why don't we check that this field theory calculation on an orbital also gives the right answer? And so this is the story. So we defined at some point a long time ago in papers by Uribe and Uribe Hikotentu, etc. All these theory of the loop spaces for stacks. Bona fide C infinity loop space, I don't mean the derived loop space. While it's extremely interesting in the derived loop space, and it's very, very interesting in the algebraic versions of this, sometimes you want the real thing, you know. Sometimes you want the real product, you know. So, you know, not this thing, you know. And blah, 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 blah. But we have this thing that is important in this conceptually. And again, it's very easy, but it's very extremely important conceptually. That is that a very fundamental part of Witten's calculation in the case of the Dirac operator and the elliptic genus and so on and so forth, from the point of view of loop spaces, according to Witten, is that the constant loops, the circle invariant loops are constant loops and is a copy of the manifold. And so you have a lot of expressions on the manifold, like the genus is an integral of the manifold, and this kind of thing. But for an orbifold, our observation is that the corresponding circular invariant loops is not the orbifold, but the so-called twisted sectors on the orbifold. So when you do this S1 invariant, so in particular circular invariant loops on the orbifold, on the stack, you don't get the stack back. If this was a manifold, you would get the manifold back. But if it's a stack, you get the inertia stack, the twisted sectors, and this is our conceptual reason why the twisted sectors appear in all these conformal and topological field theories over orbifolds in the physics literature. So this is the reason. And so we do that, and this appears in the physics literature, and a lot of the invariants with I of x are referred to as string D, and it makes sense from the point of view of loop space, of this loop space calculation, and modulo certain inversions of numbers and whatnot. This is more or less the fact that the orbifold characteristic of Conway and Thurston can be recovered from this point, from this loop space point of view. These beautiful arguments of Conway and Thurston and whatnot. And we have this important localization formula that tells you that this equivariant K theory localizes to the twisted sectors, non-equivariant. And all these are important clues, because now we expect the index, you know, the traditionally we have the index of the Dirac operator in the equivariant K theory, and now of course we expect it to occur, and now with the chain character in cohomology of the twisted sectors. That is the so-called Chen-Ruan cohomology. So now we expect a lot of this, of the action to take in Chen-Ruan cohomology for this reason and not in ordinary cohomology. And, well, and then I will not, but it's impossible to, now it's very fast, you know. And, well, there is this Deutschmann-Heckman formula. You have a Hamiltonian, you have the localization formula, you know, for the E to the H. So you add over the fixed points of the action. This is a famous localization formula for this kind of integral, and for oscillatory integrals. Again, I'm not putting the I here. Let me not do it today. So you have the Deutschmann-Heckman formula. And again, yet that further simplification by Witten is that you could use the Deutschmann-Heckman formula on loop space for this Hamiltonian, and in that case the loop space becomes a symplectic manifold whenever M is compact and orientable. It's a beautiful thing, no? Whenever M is compact and orientable, you have an orientation. automatically the free loop space becomes a symplectic manifold, and this becomes a Hamiltonian, and now you have this Doisterman-Hetman formalism. And when M is spin, the loop space is orientable, and that explains the necessity to have spin manifolds to run this kind of thing. Not only an orientable manifold, when you are a young student and you study index theorems, it's kind of a funny condition, the spin thing and taking the. But this explains why you would want precisely spin manifold and not just an orientable manifold. And this is sort of thing that should be more implemented systematically in algebraic geometry, and there are various attempts. But anyway, when you do the Doisterman-Hetman formula, you get the Atiyah-Singer index, the classical Atiyah-Singer index. And if you are bismuth and you can do the given measure, you get a proof for the Atiyah-Singer index using. But you have to translate this integral formalism to K-theory formalism, like I did at the beginning of the talk, and so you are using localization in K-theory. And this gives you a proof of the Atiyah-Singer index. If you can do a lot of probability measures, very sophisticated ones. But now now we are. This is our calculation. This is in a paper by Bernardo Uribe, Tommaso de Fernex, and Thomas Nevins. And so we do it on an orbifold, and we do it very carefully, and we do a lot of things. And you do it, you do it, you do it, you do it, you do it. And then you get, and then of course you get this thing that diverges, you renormalize it magically, and this is the point where it becomes non-mathematical, and this could be fixed by some Singer method or something. But anyway, in our paper we just say, oh, this divergent thing is equal to 2 pi, and we do it, you do it, you do it, you use we will say a function. This other divergent thing is, well, obviously, to the minus 1/2, So you take all these divergent things and do Euler kind of crazy things, and then you get the index theorem for the equivalent index theorem with this method. So we get in our paper a full proof modulo these renormalization things that should be done using some Singer method or that we don't take care of, but it should be, there should be some renormalization procedure. But we do this, and then we get the index, the equivalent index theorem, the Atiyah-Singer equivalent index theorem. And so, well, you can continue. You get it. It's called the Kawasaki formula. So we get here, we get all the way to the front with the sectors. Of course, we predicted it would be so, and of course it is so, because of localization. So, well, now we go one step further, and we take the second loop space. And now we do it again. And after a lot, now it's a lot that we get the project. And so we get the elliptic genus, and now we have to throw out 4 renormalization factors, and we get the elliptic genus as an integral via Doisterman-Hetman localization of a torus action on an infinite dimensional manifold, stack. So you get a torus action on an infinite dimensional stack, and you do the Doisterman-Hetman localization for the symplectic structure, and you get the formula. And then you recover Borisov Liebgober's definition of the elliptic genus in. So I managed to get, after all this talk, to the definition in the algebraic geometry papers. Thank you very much.
So, is the elliptic genus a variant of some sort of massive performance theory associated with Columbia?
Well, it's rather it is a partition function of a theory. It is a partition function. So it has invariance of the theory. It does have invariance of the theory. But of course, it is a power series and letters, lots of letters there. And notice that here in this calculation, the so-called age or degree shifting appears. So it's really in the general universe. It's not just in the topological K-theory. It's really, when you do this, really this thing appears. And this appears because we are using this normal bundle information from the symbols in this calculation. You know? What they call the symbols these days, we call it something else. And well, it's not identical, but it's extremely related. And again, a clarification on the relation of this normal bundle information. Here we're doing the normal bundle calculation. That is the information that is inside the symbols. So it's the same information, but organized slightly different. But again, we get a, let me say, a birational invariant, or well, actually a K invariant. So we get a K invariant. Rigorous proof of this is Boris of the Gober in the annals, and we have a non-rigorous proof of this, but we throw all these renormalization factors, and we use all these probability measures that already were hard at the one loop space. Probably it's not harder at second loop space, but anyway, we really didn't went to all the legwork to produce a rigorous proof. We just provided a mathematical physics argument. So there is invariance, yes, there is invariance all over the place, and there is the number 12, and in particular, of course, there is this information of the spectrum of a singularity for certain singularities. So there is, because the spectrum is about these charges, is not the thing, but information that evaluations here and coefficients here and things here can give you invariance. But this has a very nice birational behavior.
Other questions, yes?
What's the reason for going to the double loop space?
Well, because, you see, the index of the Dirac operator, the Thiasin index is the EHA genus, the Thiasin index is the index of the Dirac operator on loop space. But the elliptic genus is the EHA genus of the loop space. So you have to do the Dirac operator on the double loop space, the index of that Dirac operator to get the elliptic genus. And this is not totally apparent in the approach at the beginning of the talk, where there was where you have kind of, from the one hand, the rigidity of G, and on the other hand, the representation of the diffeomorphism of the circle, and then the modularity was not obvious at all, it was a calculation. Here, if this theorem was true, the modularity would be obvious, because now you have, it's an elliptic curve going into the manifold. So it's the space of an elliptic curve you map it into the manifold. And so you have this tau, the parameter of the elliptic curve, and now you have the various, the elliptic genera. Here I don't have the tau, because the tau is implicit in the calculation. But because now it's obviously modular. Now the modularity is transparent. And this is not a, and the other approach is not, it's magic, it's, wow, it's modular problem. Here is transparent modularity.
May I ask? Thank you for your interesting talk. And please do consider commutative or non-commutative elliptic curve.
Elliptic, and non-commutative elliptic curves, no, we haven't considered that at all. But of course, we have not considered that at all.
Excuse me, you consider commutative elliptic curves?
Yeah, just normal, classical elliptic curves.
And probably this is in framework of atom. Probably you have to quantize elliptic curve or not.
I don't know, you know. I don't know. It's clear that the atom theory produces some of the information of this story, or all of it, who knows. And this story therefore produces some of the information from the atom theory. So a conceptual understanding of the relation of this conformative theory to the theory of atoms would be good. And of course, now, once you go full conformative theory, then everything is non-commutative, and uncertain in the atom theory, is non-commutative structure, etc. But I just don't know. There is a lot to clarify. This was just a improvised talk, just to offer some intriguing possible questions.
Thank you. But elliptic genius, it seems, connects with formal groups connected with elliptic. This is not my question. Next question. Do you listen about elliptic genus, or its analog for non-commutative elliptic curves?
I know nothing about that.
Thank you. Thank you.
Other questions? If not, let's thank Ernesto. So we continue in 25. So let me just say that after the last talk, you are all invited to the Pantev Institute, which is going to most likely be here on this floor or on the second floor. All right, we continue our morning session with the Paul by Johnson, who's going to talk about new type of posture. John?
Yeah, thank you. Let me write down my file. Okay, so thank you very much for invitation. So it's always great pleasure and privilege to visit this wonderful institute. And actually, this story, this is joint work with, basically joint work with Ludmil and Ernesto. Okay, which actually started here 2 years ago. So, okay, let me start. So, in order to explain our motivation, let me briefly introduce the notion of row transformation. So in 1960, Kaehler introduced this notion of row transformation. So actually, this row transformation appeared many times in this conference, but I think, as far as I see, all these row transform is, in our point of view, generalized row transformation. So let me introduce, just to recall the definition of original definition of row transformation introduced by Kaehler. So let S to C be an elliptic surface. This, and so just means that I have an elliptic surface to a curve, and let me choose a point P where this this net is smooth. So it means that it's just smooth elliptic curve. And then I choose a small neighborhood delta containing P. So let me choose a small neighborhood delta, which is just point in C, such that this has a small neighborhood. And then I consider its inverse image, and it's it's small, and then obviously this S is nothing but inverse image of this small neighborhood, and inverse image of this C minus this point. So I will call this as delta, and I will call this as star. Okay? So obviously, this elliptic surface can be decomposed into two parts. And then I do analytic operation. So I consider this, this tilde. So this delta tilde. So I consider this MTB1 map, cyclic covering, which stands from y to the n, and then I, then I pull back this elliptic vibration over this small disk. So this is this is a small disk, and this I consider this m to the 1 ramified m to the 1 cover, and then pull back this elliptic vibration to over this one, this vibration, and then obviously there is a G mod n action here, but I twist this action a little bit. So I twist this. I mean, this is a, this is obviously on the base there is a G quotient m action, but I choose a order m point. So since this is small disk, I choose order m point on each fiber, and it's kind of section over here. So then I consider another action on this G quotient m, which sends y to y G to this e to the 2 pi I over my times G plus 1 so like this. So I mean I twist action. So this action is not only rotating this base, but also move this this zero section to the order m point. Okay. Then I take. So then I have this new action. Then I take quotient of this elliptic vibration over this base. Then I obtain another elliptic surface over this base, and then you can see that. So for each point, like here, actually this action is rotating. This action moves this fiber to this fiber. So what I mean is that for each point which is not the origin, this action is free. Okay, but on this zero, actually this base action is trivial. So only this action, this GM action, is translating this point to here. So if I take quotient of this elliptic vibration by this action, then everything is the same. I mean not same, but everything. I mean this fiber, this action is free. So this fiber is identifiable here. But over this zero, there's multiple fiber over order m. So this becomes multiple fiber over order m. And the upshot is, let me call this the new elliptic vibration over the space to be this. Sorry, yes, that. And then on upshot is there is a analytic isomorphism between there's an analytic isomorphism between this S and I take out this central fiber, and there's analytic isomorphism between this guy and this guy. So what I mean is I take the central fiber, and then one can identify this this elliptic vibration, taking out this central fiber and this guy. And then I glue.
Is it possible to change the chalk? We cannot see it.
Sorry.
You need to wait
I think it's
until
this way.
you need to wait until it's dry.
It's dry,
Yeah, sorry. I mean, okay, then let me erase this and wait this.
But use the
the dry one.
Dry one.
No, top. More on top.
The blue.
Thank you. Yeah, but anyway, let me use this. Thank you. Yeah. Thank you very much. So I glue this guy, and there's another isomorphism with this guy and this guy. And then I glue this guy with this guy and this guy. So I obtain new elliptic vibration, so called as M, by gluing this part and this part. And then this is a new elliptic surface. Which has now multiple fiber over this P, multiple fiber over that. So let me call this to be, and this is called logarithmic transformation. So I will call this to be log transformation. Of S. Okay, then one can actually this log transformation has playing very important role in many areas of mathematics. For example, let me consider give you one example. So I consider P2, and I consider two elliptic surface, pencil elliptic surface. So I have P2, and I have one elliptic surface, and the other elliptic surface, P2, and then I for generate when two elliptic surfaces meet transversally, then this meets at 9 points. Then I blow up this 9 points of P2. Then then this gives you elliptic vibration given by this pencil generated by this E1 and E2. So I have this elliptic surface over this guy, and then so I have a blow up of 9 points of P2, and I have an elliptic surface, and then I choose 2 points. And I do log transformation of order 2 and order 3. I do log transformation, and I make multiple fiber of multiplicity 2 and multiple fiber of multiplicity 3. And I obtain this as 3. And this is called the Dolgashev surface. And actually, Donaldson proved that. So before going to Donaldson's theorem, by Prisman's theorem, you can see that this. If you compute Hodge number of this guy and this guy, the Hodge number of this guy is 191. One pen 1. And the Hodge number of this guy is also 110. And by theorem of quadratic form, you can see that, and by work of Friedman, you can see that this guy and this guy are homomorphic to each other. So this Dolgashev surface and P2 blown over 9 points are homomorphic. Homomorphic to this Dolgashev surface. But there is a theorem, very famous theorem by Donaldson, who says that actually this P2 blown on 9 points are not diffeomorphic to this Dolgashev surface. This is one of the first examples where one can find homomorphic surfaces which are not diffeomorphic to each other. So, there are lots of stories related to this, but I want to mention that, so this actually result says that there are lots of similarity between these two, but also non-similarity between these two. So, actually, let me give a small remark, is that log transformation is not algebraic operation. Log transformation is not an algebraic operation, which means that if you start from algebraic surface, but if you do log transformation, sometimes the resulting variety is not algebraic anymore. So this is not algebraic operation. So it makes quite hard to, for algebraic geometry, this reason makes it quite hard to understand what's going on with algebraic variety. So
Because it was wet.
yeah. Use this. Okay.
All of this is dry.
Yeah, I will wait.
You can just wait.
Yeah.
Wait your minutes.
Wow. Okay. So then.
So what is this comment that it's not an algebraic information? Transformation. I don't understand it.
In general, what I mean is it's very hard to, as you know much better than I do, but it's very hard to track how algebraic information here transforms to algebraic information here.
No, but for all what you have described, they are all algebraic.
Right.
You cannot try them as a intersection of equation. Nobody knows, but they still are like that.
These case, both of them are algebraic. That's true. But what I want to say is it's hard to find a general procedure which keep tracking algebraic information here to algebraic information here. So
Yeah, okay. You cannot write them as we don't know how to write them as zeros of polynomials, but
right.
maybe someday.
Yeah, exactly. Yeah. So as you mentioned, it's hard to write down the equation of this and find moduli of this. It's very hard in general. Okay, so yeah. Anyway, so we know that this and this are not developing to each other, and then let's consider the derived category. Since both of them are algebraic surfaces, I can make perfect sense to talk about derived category of this surface and this surface. So conjectural picture here is that if you consider this bounded derived category ownership of this Dolgachiev surface, then there are always 12 exceptional collection, like 12 exceptional collection, and it doesn't generate, and it is expected that this doesn't generate the whole category. There must be some so-called phantom category. So which satisfies this, which is not detectable by additive invariant. For example, the Hawkshire homology of A is shallow, and this cross and equal of A is shallow. And by Orloff's result, you always know that derived category of this rationality surface has, not this one, but exceptional collection of times 12. So for rational analytic surface, there are 12 exceptional collections which generate the whole category. But for Dolgachiev surface, it is expected that there are length 12 exceptional collections, but it doesn't generate this, will not generate this whole category, so there must be so-called phantom category, which is also organized to this time.
Do you expect that this has anything to do with this things not being diffeomorphic? Or?
Yeah. Well, I think it's really meaningful to expect. Teach me this. This phantom category is kind of obstruction of this suffix to be rational. So it's kind of some mysterious invariant which prevents this Dolgachiev suffix to be a rational suffix. We don't have any actual proof for that, but I think it's common belief. Yeah. For non-rational surface, this is not general. there are recent development in this direction, but I will not talk about this today. Okay, so, and it is not only conjecture, but there is a theorem by Yong-Ah Cho and Yong-Lam Lee, and they found some Dolgachiev surface which actually have this semi-orthogonal decomposition, and recently Liang and Ludmil also proved that, found an example, there exists certain Dolgachiev surface with this expected semi-orthogonal decomposition. But we do not know if this holds for every Dolgachiev surface, but anyway we have some evidence that so there are some Dolgachiev surfaces having this expectation. Okay, then, so this category has found something like in around 2013 or 14. So now it's 10 years after first discovery of this phantom category. But unfortunately, as far as I understand, we do not know how to approach this, on how to understand this category. So people believe this is obstruction to rationality and blah 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 blah. But we still do not know how to understand this line. So I want to consider. We want to suggest approach to understand in this category in terms of gross-ending of variety. So let me, actually this also appeared many times. So let me definition. So I consider let P be an algebraic variety over C, and I consider this gross-ending of varieties over B. So this is a free abelian group generated by an isomorphism class of algebraic variety. So this is algebraic variety over B, and I take, this is free abelian group generated by this algebraic variety. Then I take equivalence relation. So this X is equivalent to X take G and plus G, where G is, because everything is over B, is closed algebraic variety over X. And actually this becomes a ring if we take product to be the fiber product over B. Then this becomes a ring, so I will consider this to be gross-ending of variety over B. And then, why we consider this thing? Because it is believed that, this category is very mysterious category because we can't see this via Hochschild homology. We can't see this via, this gross-ending group. And also, one can show that this rational charm motif of this class is same as the rational charm motif of this one in the category of rational charm motif. So this cannot be seen in in the level of motif, Hochschild homology, and gross-ending group. But still, there is hope that one can see this via gross-ending of varieties. Why? Because there are also remark that there are examples that exist on algebraic variety x1 and x2 such that they are bounded their category of this guy is equivalent to this bounded category of x2, but the gross-ending this class is not staying in this class in the gross-ending over variety. So here the base is point. So I just hit to the point. So this is absolute case. So in this sense, one can see that this gross and linear variety is a little more sensitive than derived category itself. So there's a chance that this guy and this phantom category can be seen in the level of gross and linear variety. And also, it's quite important to see the difference between because there is a theorem by Garkin and Sindel who proved that if this L is expressible affine line is a zero divisor in gross and linear variety, then generic cubic purport is not rational. So, yeah. So I mean, although actually I will explain this soon, but although later actually this turned out to be zero divisor, but I mean this approach actually showed that there's some way to understand bidirectional geometry in terms of the sky. Wow. So
With the wet and the
yeah. Okay. So I should do. Okay. Then.
What does it say? That if it is a zero divisor?
If it is zero divisor, then.
But it's probably not a zero divisor.
That is not a zero divisor. Sorry. This is not a zero. Sorry. If this is not a zero.
Yeah, that.
Thank you. You are right.
That's helpful. Yeah.
Yeah. If this is not a zero divisor,
Yeah,
then generic cubic purport is not rational. Actually, they made some argument to prove this. But
There is a proof that it's a zero.
yeah, actually, I was going to that. Thank you. So, but after this theorem motivated that Burstow, and he proved that actually L is zero divisor. In gross and linear variety. And the way he constructs this zero divisor is, the difference. The way he found this, to prove this theorem is quite interesting because he first found two Calabi manifolds. Some Calabi manifolds having equivalent derived category. Then he saw the difference, measured the difference, and then he found that this times L times something which is not zero is zero. So yeah, and the way he found is having found two variety having equivalent derived category, and the difference gives the zero divisor here. So in this perspective, one can see that. So in this case, there's no difference between this category and this category because these are same. So then this gives a non-zero divisor, non-zero divisor in this gross and linear variety. Let's try. Wow. Okay. Any questions so far? So, and actually there's a conjecture by Sasha and Gini, and Sindel asking if x1 and x2 are algebraic variety such that the derived category of x1 is equivalent to the derived category of x2, and they conjecture that the difference becomes a zero divisor. divisor in gross and linear varieties. So anyway, so in this perspective, it's quite interesting to see the difference between this rational elliptic surface and this Dolgachov surface, and what we can say about this. But this is obtained by log transformation, so we can. So it is maybe somewhat easier to consider this difference in the level of gross-ending ring over, gross-ending ring over base. So let me give this down. So let S be a elliptic surface, and let IM be its log transformation. Then, what we can prove is, but in order to say these two are, belong to the same thing. So if this S and SM are algebraic, both algebraic, then you can see that the difference is a zero divisor in gross-ending ring of varieties over C. So if you consider, gross-ending ring over base, then actually one can see that the difference is indeed a zero divisor in the gross-ending ring of a variety of C. So this, in some sense, provides us the way to understand the phantom category in the level of gross-ending ring of variety. So this is not zero. The important thing is this is not zero, but this is non-zero zero divisor in gross-ending ring of a variety over base. So it gives some way to understand this is somewhat way to see how phantom category should behave in the gross-ending ring of variety. Okay. Any question so far? Okay. So I have 7 minutes now. So please recall that I mentioned that log transformation is not an algebraic operation in general. So I want to, in some sense, we want to erase this assumption. We don't want to say, we just, in order to state this theorem, this S and SM should be algebraic variety. But in general, we don't need this, log transformation in general doesn't need to be preserve algebraic category. So, in this sense, I want to extend the gross-ending ring of variety to cover general compact complex manifold, and study what happened when I consider the difference between these two. So, to say that, I need to give some example. So there is so-called okay. So yeah, I wanted to discuss this. So then, to find a reasonable, reasonable extension of this ring, I need kind of definability. So let me explain the notion of O-minimal geometry a little bit further. So, definition. So a collection structure if it satisfies the following condition. So satisfy first Sn from a Boolean algebra or subset of Rn, and if A belongs to Sn, and A times R belongs to Sn plus 1, and of course R times A also belongs to Sn plus 1, and well, actually these are some conditions anyway. I mean, this guy Sn for each one and actually this first condition is the most important condition, and the first and fourth are most important condition. So if A belongs to Sn plus 1, then find A belongs to Sn for every linear projection of 1 plus 1. So let me repeat the definition. So for each n, for each integer, I collect, a subset of Rn's, and I will call this collection of subset to be a structure if it satisfies this condition. The especially important condition is this first one. So this Sn is form of Boolean algebra of subsets of Rn, and the first condition is if this belongs to here, so this means this is certain subset in Rn plus 1, and its projection belongs to this one. Okay? And if this structure satisfies the following additional condition, then I will say this to be O minimal structure. So structure S is O minimal if for any x R, this x belongs to S1, and this x y R2. Well, this is S2, and again this is one most important condition again. So S1 consists of finite unions of open intervals and points. Okay? I mean, a collection of the subset structure is called O minimal if the point belongs to this guy, and this given by inequality belongs to here, and if S consists of this one-dimensional, if the subset of this one-dimensional consists of a finite union of all three interval points, then I will say this structure to be an O minimal structure. Okay, then I can do kind of geometry using this O minimal structure. So then using this notion of O minima, I can define definition of subset of set A in Rn is definable if A belongs to this Sn. So this is collection of certain subsets in Rn, and if this subset in Rn belongs to this guy, then I will say this is definable. and a function f from A to B in Rn and Rm is a function is definable if its graph is definable. Okay, so then I consider certain class of a function and certain class of set. Then I can do geometry. So then I can, using this notion, I can consider O-minimal geometry sense. So then I can do kind of O-minimal geometry. So there's a, for example, so let me give several examples. So for example, if I consider this n as n to be given by so what I mean is that so a set A in Rn is called semi-algebraic if this A can be given by finitely many some equality and inequality of finitely many polynomials. So I mean A is given by some f1, f2, fl is equal to 0, and g1 right to this guy, and g2 this guy. Well, this inequality. So then I consider Boolean algebra generated by this set, and on subset, I mean obtain kind of Boolean operation of this type of set is called semi-algebraic. And one can show that actually this semi-algebraic is O-minimal. So there's theorem by Kasky and Seidenberg says that semi-algebraic set forms on O-minimal structure. And actually, there are, I mean, a bunch of other examples of O-minimal structure. So one can actually add, I forgot very important thing. So this Fi and Gj are all polynomials. Sorry, this is most important. So I consider only polynomial functions. And I consider subset given by equality of certain polynomial function and inequality of certain polynomial function, and I do some Boolean algebra operation. Then this is called semi-algebraic set, and then you can prove that this semi-algebraic sets form an O-minimal structure. And you can add exponential function here. So this is called O-minimal structure called S algebra. So this is O-minimal structure of semi-algebraic set. And you can add exponential function here. And so what I mean is that you give this kind of relation and some exponential function involving this guy. And then one can show Ricky's actually proved that if you add real exponential function, this also form O-minimal structure. So this is Ricky's. And you can also consider sub-analytic set, sub-analytic functions. Sub-analytic function and Boolean algebra obtained by sub-analytic thing. So then you obtain this guy, and you can find some common extension of this guy. So these four are very standard O-minimal structure, and actually there are more O-minimal structure, but anyway, these four are very studied. And actually, with this talk, we will concentrate on expansion of this O-minimal structure. So then, why this minimal structure is important? So I have the following theorem. The minimal structure is kind of, prevent some complex analytic set, to be crazy in a sense. So let me explain what I mean. So there is a theorem by Tozel and Stashenko. Where is it? Zero and Stashenko. Stashenko proved that if you consider some analytic, this is really amazing theorem. So I consider some analytic subset in Cn, so which is given by some dancing of certain holomorphic functions, in this Cn, and suppose that this is definable. So I mean, but if this is, but you can consider this is R to N. So anyway, this is a subset here, right? And if this set is definable, then they prove that this is actually algebraic. This is only mature. So if G is definable, then you can see that G is actually algebraic. So this is kind of, I mean, this condition, this definability is somewhat, looks strange, but it has some aspect that this makes some analytic space to be a tame space. So actually, it's kind of making this analytic space behave looks like algebraic properties. Okay, then we have a theorem. So why consider this thing? So I consider the Brooks-Henry ring of the definable analytic space. So this is free abelian group generated by isomorphism class of where X is compactifiable of definable analytic space. So I consider this compactifiable definable analytic space isomorphism class of this guy, and taking this equivalence relation again. So where this X is equivalent to X take power G plus G, where G is definable, analytically closed subset of X. And then I give this this relation. Okay? Then this becomes I will say this is the Brooks-Henry ring of definable analytic space, and this is sufficiently big enough because if I consider so from now on every O minimal I consider sorry, my handwriting is getting worse and worse. Consider expansions of analytic this guy, and then there's a theorem by Tozel and Stashenko. Prove that when X is complex manifold, then this is definable. This is definable over its O minimal structure and its expansion. So this ring is quite big enough to consider all could contain. So it's enough to it's big enough to so it's containing all complex manifold. And this I can define this Brooks-Henry ring overarching this way. Then I can make an analogy for this ring. So there's a theorem. I mean, we can prove the following theorem. So then, because this containing all compact complex manifold, so obviously it also contain non-Caehler manifolds too. So we can actually prove that if you consider this let H, so whenever I have a compact complex manifold, then there's canonical, not canonical, but a well-known homology theory, so which is known by A-free homology, and Both-Chern homology, and Dolgov homology. And all these three homology theory coincide when these are all the same when X is compact, X is Caehler. So in Caehler manifold or algebraic variety, there's no difference between these three, but these three actually become diverse and become different when this becomes non-Caehler manifold. So our theorem, theorem is if I choose any of this guy, so I consider that H be any of these guy, and for X be a compact complex manifold, then I can define Hodge polynomial of P and Q for any compact complex manifold. Then what we can prove is this there is this Hodge polynomial is actually a ring homomorphism from this to this G. So this becomes a ring homomorphism. So this is kind of a motivic measure extended to outside the world of algebraic geometry. Anyway, these three, and actually more. If this satisfies certain condition, then we can prove that this actually induces a ring homomorphism from this corresponding ring of definable analytic space to this. Okay. So any question? No question. Okay. So then we again want to discuss what happened to log transformation. So we have some sufficient gadget to understand the log transformation. So since whenever I have some elliptic vibration over space, and suppose that this is torus vibration, and I do kind of generalized or an ordinary log transformation, then you can ask, okay, what happened to this guy and this guy? So actually, what we can prove is that the difference is zero divisor in cross-and ring of definable analytic space. Okay, so we cannot generalize our previous theorem to say that to measure the this phantom category can be definable analytic space over base. So we somewhat generalized our previous theorem of discussing the image of phantom category. Kind of image of phantom category in the cross and ring of variety. And we generalize this by considering arbitrary log transformation, generalized log transformation under certain conditions. So let me not write down the precise condition, but for certain condition we can prove that this guy actually gives zero divisor. So let me give you one evidence of this story and we'll finish. So indeed I'm not an expert in this manifold, but luckily I have Roland and Ludmil and Ernesto, who are best expert, all of the best experts in this thing. So I consider so-called the LBM manifold to give an example. LBM manifolds. So these are some of sorry, just one second. So LBM manifold is defined in this way. So and actually it's generalized by Rosio. Sometimes people say it's LBM manifolds. So anyway, let me give a definition. So let gamma 1, gamma 2, gamma n be configuration of n vectors in Cn and let H 1 so lambda n be the convex hull of lambda 1 n. So what I mean is that I consider this this n vectors in Cn, so I consider this Cn and I consider this lambda 1 and lambda 2 and blah blah blah. So this n vectors in this guy, and then I consider this convex hull. I mean, I look at this guy as R to M, and I consider this convex hull generated by given by these vectors. Okay, and we say if gamma is admissible, say this gamma is admissible if it satisfies certain condition. Let me write down this condition. Let's talk about Categorical condition and weak hyperbolic. Then I can, if this satisfies this condition, then I can consider some kind of action on the Cn by Cn given by this Cn times Cn goes to Cn, where this key z goes to this z1 exponential of gamma t1, gamma 1 t1. Wow. This is inner product, and Zn exponential gamma n. So anyway, I have this Cm action on this Cn, and then it gives kind of foliation on. It's something like a GIT. So I consider this group action on this space. And then I pick out some bad point as I always do in GIT case. And then this gives a kind of foliation on this Pn minus 1. So this gives a kind of foliation in Pn minus 1. Then using as a lip of this foliation, I can construct the so-called LBM manifold. So if this LBM manifold is controlled by some combinatorial data, so let me give one example and finish. So I consider, so I can regard this Airbnb manifold as kind of quotient of a certain action here. So then if I consider this C star, C2 minus point, and I consider this C star L. In this way I can obtain this Airbnb manifold, and then I can regard this as a quotient of a certain. I can identify this manifold as quotient of for some cases. So some cases I can regard this as a kind of this one model, some kind of geometry. So if I take quotient, then let me obtain this kind with this HM, and I will call this Katzarkov of manifold. And the point here is, if M is big enough, if M is sufficiently large, then its Dolbeck cohomology, actually we explicitly compute this Dolbeck cohomology, actually behaves like this Hawk surface. This is why we call it Hawk surface times this Hauch-Delin polynomial of this elliptic curve times -1. So we have some. We can. This is this is non-Caehler manifold. So actually, there's no reason that these guys behave like algebraic variety, and there's no explicit geometry relation between this and this. So this is kind of adding some job on this and to make. So there's no classical geometry relation between this and this, but in terms of Hauch-Delin polynomial, this looks like this one. And we proved that in our actually theorem gives a certain case. I don't claim this is conformal case, but for certain case, actually this reason this is why, because this guy and then this times need to be n-1 is a check. Defined over analytic space. So this is why we believe that this is why this guy, the difference, this guy and this guy actually will typically behave in the same way. So anyway, we provide a bunch of such example in our upcoming paper. And let me stop here. Thank you.
Questions?
At some point in the talk, you had this three types, Dolbeck homology, Borchardt, and where did that play a role? I think I missed. Where did those three types of homology play a role?
Actually, it was. Actually, Tony asked when we developed this, begin to, in early stage of our development. Actually, we discussed with Tony, and Tony asked us that for non-Caehler manifold, there are three natural homology theory. And what is the one motivating measure, in a sense? And what we prove is actually all of three are canonical in the sense that all of them gives motivating measure. So that means, actually it doesn't need to be three. So if this homology satisfies certain blow formula, which we discussed, and the blow formula and the QNS formula, then it's automatic that this cohomology theory actually gives motivating measure. So actually, it's very interesting question that how to understand this divergence of this three cohomology in terms of motive. Actually, we don't know about that. It's an extremely interesting question, though. For algebraic manifold, they are the same, so we cannot see the difference. But this is new phenomena for non-Caehler case, which we haven't able to understand.
So you can expect to recognize this Delta-Var lemma in terms of these different motive cohomology somehow? To relate this to three different cohomology theories. Because you said that these three different gives different motive measures, right?
Yeah.
And there is Delta-Var lemma to relate these three cohomologies.
So what I mean is that when Delta-Var lemma holds, then all these three cohomology behave the same, exactly the same. So what I mean is that, you know, this, so actually this is question. So we have this closing ring of will definable to this guy. And there is a closing ring of algebraic variety here. And there is you know, this closing ring of this delta bar guys, right?
Yes.
So I mean, here and here these are, you know, exactly the same. So this guy is kind of, so if you, I mean, you know, if you have two ring homomorphism, the difference doesn't mean to be ring homomorphism. So it's somewhat, you know, complicated. But I mean, but anyway, these two guys are, you know, where these three guys all behave the same. But actually, this become different for general case.
And it's indeed a kind of Grothendieck ring. It is from the delta bar, like it forms a Grothendieck sub ring.
Yeah, this form a certain, you know, subring. Yeah. So there's kind of stratification of Grothendieck ring of variety. So which mysterious. I mean, everything is mysterious there at the moment. But I mean, yeah.
You mean the other way around? I mean, algebraic varieties are all.
Sorry. Yeah. Right. Right.
All right, let's take John again. There's a lunch in the usual place, and we go to
Yeah. I'll say a few more remarks on this result. Namely, here we don't assume anything about the location of these singularities or the number of these singularities. No condition on number of singularities. Okay, and to complement this result,
maybe the question is what about the location of the points, well, compared to general positions or things like that? Does it matter?
For this theorem, it doesn't matter at all. What matters is then certain combinations or locations or number, they might not be factorial anymore. I'll say about factoriality also mentioned. So one result to complement this is that general sextic double solids that are Mori fiber spaces over a point are not birationally rigid if it has a CAK singularity where K is B. Point are not birationally rigid if they have a CAK singularity where K is bigger than 3. And we conjecture that sextic double solids that are Mori fiber spaces with CA1, CA2 with only these singularities, that we conjecture that these are birationally rigid. So I'll say something about the proof. So this is local inequalities.
Excuse me.
Yes.
Is there a number of bounds for singularity?
Yes, I'll write the bound. So I'll write the sextic double solid has at most 65 singular points. Singular points. Yes. If I remember correctly, 64 is an old result, and to get 65, they used something called coding theory, or theory of codes. So this is very non-trivial.
So the 65 are all nodes?
In the examples that they've constructed, yes, that they're all nodes. But, yes. But probably, yeah, I'm not sure if they have to be nodes. But in the known examples, they are. Okay, so the key step in proving this result was a new local inequality. So before I state it, I'll say about the method of maximal singularities, the philosophy behind this. We say that at the tensorial contraction, phi from y to x, where x here is a Mori fiber space over something. This is a maximal extraction if there exists a mobile linear system M on X such that the pair X, comma 1 over n M is non-canonical along the exceptional prime divisor E of the divisorial contraction. And here, this n is a positive rational number such that every divisor in this mobile linear system is Q linearly equivalent to minus nkx. So the anti-canonical divisor times n. So this is what that maximal extraction is, and the image or the center of this exceptional divisor E is called a maximal center. And why we're interested in maximal extractions and maximal centers is the following: the Noether-Fano inequality. Noether-Fano inequality. So this says that if X is a Fano variety that's a Mori fiber space over a point, X Fano variety which is a Mori fiber space over a point, that means it's Q factorial terminal at Picard number 1. Then X is birationally super rigid if and only if X does not admit a maximal extraction. Does not admit the maximal extraction. Okay, so now I'll state the theorem, the new local inequality. This is a generalization of Buklikov's 4n squared inequality, which was extracted from the work of Iskovsky and Manin. And it generalizes it from a smooth case to this singular case with CA1 singularities. This is also together with Krylov, Okada, and Park. So let M be a mobile linear system of Cartesian divisors a positive rational number. And now let's assume there exists a maximal extraction, and then we'll have a local inequality. So let P in X be a center of non-canonical singularities. Non-canonical singularities of the pair X 1 over n. If you take two general members of this linear system, let d1, d2 in M be general. And then we have an inequality. So I'll write it down this way. Then we have an inequality that if P is a CA1 point, then multiplicity at the point P of this intersection class intersecting D1 and D2, this is greater than 2n squared. So here P is CA1 singularity. That in the smooth case we have a 4n squared there. And I'll also say a more recent result that we're currently working with Caehler Okada is if P is a CAK point, then we'll have here 4 over k plus 1 n squared.
So and here and there are different ends, yeah? So this n is CAN, and you also have n, the coefficient of the...
so this is CA1 here. CA1 and CAK.
So CA1. And n is this rational number.
Exactly, n is this rational number here.
So does this statement have a low canonical threshold interpretation?
So these, I guess, if we're talking about canonical things, maybe it's a canonical threshold description.
Threshold.
Yeah. But, and this formulation is also very close to some case stability statements. And there's a conjecture that birationally rigid varieties are case stable, but these are proved only under some stronger hypotheses. Birational super rigid varieties with some invariant, at least certain value, then they are case stable.
Well, you don't know if these are case stable.
This one I'm not sure. Yes, this one I don't know. Yeah, that would require more work. Yes. But yeah, the conjecture is that they are. Okay, so and here k equals 0, this corresponds to the smooth case. So we can think of CA 0 singularities as smooth points. And in this case, it directly generalizes the 4n squared inequality. So, and I'll show how to use this inequality. But even if you're not familiar with maximal abstractions, then this, together with Noether-Fano inequality, it's easy to apply it. So, applications. solids.
Excuse me, so 1 over n m is not necessarily Q equivalent to K canonical class. So it's just
Here it's not necessarily, but I'll only use it in the cases where m is Q linear equivalent to minus nkx. So application is like this. So let's look at the Symplectic double solid, which is a Mori fiber space over a point. Then we Q factorial and terminal. So X Q factorial terminal Symplectic double solid, and assume a CA1 point is a maximal center. Okay, then what do we do then? Then I'll continue on this part. Okay, then just applying the Ludwig inequality, we get that d1 times d2 times some general hyperplane, that this is greater than 2n squared. On the other hand, we know d is minus nkx each di, and the general hyperplane, that's linearly equivalent to the anticanonical divisor. So this is minus kx cubed times n squared. This is the anticanonical degree of Symplectic double solids, and we know that that's equal to 2. And we get the contradiction. So no CA1 point is a maximal center. So this was the main difficulty in proving irrational rigidity of singular varieties. This is not the complete proof of irrational rigidity. So you still have to rule out other maximal centers. So that's more extra work. But yeah, this was the application of this inequality. So I'll say some more applications. So I'll go to Del-Penso fibrations. If there are any questions throughout the talk, you can ask. I'll do my best to answer. So this is with the same co-authors that we look at Del-Penso fibrations. These are morphisms to P1, and the general fiber is a smooth Del-Penso surface, and I'll look here only at degree 1 Del-Penso fibrations. Let this be degree 1 Del-Penso fibration. With only CA1 singularities, isolated CA1 singularities. And then, if X satisfies the K squared condition, then it is irrationally superrigid. Superrigid. addition, that's that square of the anti-canonical divisor is in the interior of the Mori cone of curves. And here, for this, we prove a local inequality that's a generalization of the Corti inequality for CA1 points. It's a bit more technical than this inequality here, but of the same flavor. Okay, and next I'll talk about weighted complete intersections, so more applications of these inequalities.
Excuse me, so you talk about modified the space over the point of vectors, and what about conic bundles?
We haven't yet found applications for conic bundles for this, but I haven't looked into that much. I don't know if there are examples of birationally rigid conic bundles or so I don't know the answer. Okay. So next it's weighted complete intersections. Complete intersections. And these ones I'll abbreviate WCI. So here, when I say Fano variety, so I'll assume something on the singularities. Just for abbreviation, I'll assume that these are Q factorial terminal and so Q factorial terminal projective variety such that the anti-canonical divisor example. Next I'll say a variety is prime if the class group is isomorphic to the integers generated by minus kx. And we say these are quasi-smooth. So this means the weighted affine cone is smooth. This, if I'm correct, this should imply that they're smooth as a stack. But what I care about here is that this implies they have only finite cyclic motion singularities. Finite cyclic motion singularities. There is a classification of quasi-smooth prime weighted complete intersections. Classification, namely, there are 95 families of hypersurfaces. Hypersurfaces in weighted projective spaces. 85 families of codimension 2. Of codimension 2 weighted complete intersections. And there's a family which is the intersection of 3 quadrants. X2 to 2 in P6.
So you're talking about threefolds, Fano threefolds?
Yes, Fano threefolds in dimension 3. So this is dimension 3. Fano varieties that are prime and quasi-smooth. There are some extra conditions that are required here. For example, we look at only well-formed weighted hypersurfaces, and we are not including the ones that have a small degeneration to a hypersurface. But apart from those issues, it's complete. And the partial rigidity of quasi-smooth such varieties have been studied. So here, if they are quasi-smooth, then irrationally rigid. Here, other than one example, other than this example is a complete intersection of degrees 2 and 3 in P5. If quasi-smooth, it's quasi-smooth if and only if belongs to specific 18 families. Belongs to 18 families. And for the last family, a general member is birationally rigid if it's quasi-smooth. So this gives a big list of families for which we can try to prove birational rigidity with more complicated singularities. That, or the goal or philosophy would be able to handle birational geometry of arbitrary terminal 103 fields. So this is a step towards this, or a concrete result. So
this, you mentioned two cases. Do we know what is rational and what is not rational?
I'm not entirely sure. I'm not entirely sure. So for the hypersurfaces, we know they're birationally rigid, so very non-rational. And here, I would expect they're all non-rational, but I'm not sure. So we have a theorem that 78 families of hypersurfaces and 18 families in codimension 2. In codimension 2, weighted complete intersections with only CA1 singularities and cyclic quotient singularities. That these are birationally rigid. Okay, and here, I guess we assume Q factoriality. So we look at the ones that are Q factorial and terminal. And I showed earlier an inequality for CAK points. So for this one, it's longer to state. So I'll say here, so this is a ongoing work with Krylov, together with Krylov and Okada. So I'll state it like this. From the above, 95 families of points. No CA point is a maximal center. For nk number of families. So we allow only singularities CA1 up to CAk, and then nk of them, for nk of them, no CA point is a maximal center. And then I have a big table of what are the values of nk. So for k equals 1, we have 89 families. For 2, we have 54, 53, 18, 18, 10, 10, k equals 12 up to 15, we have only one family. So, yeah, this is excluding the CA points as maximal centers, and then there would be more work to prove biaxial rigidity. So, but now seeing this, even if we have a statement, I'll write what this family 15 is. So this family 15, this is of weighted degree 50 inside the weighted projective space with weights 1, 7, 8, 10, and 25. So even if we have a statement, all of these varieties with CA 15 singularities are biaxially rigid, it's not clear if that's an empty statement. It's not clear a priori, do there exist such varieties of CA 15 singularities. And moreover, it's even more difficult to prove factoriality of varieties with complicated singularities. So I'll say a few words. So positive results in this direction. Factoriality. So we have for sextic table solids, I showed that there are 11 families of sextic table solids with CA singularities. Draw a small picture. So K is the CAK, and then this is the expected dimension of the moduli space. We have 67, 64, 60, and this is an arithmetic sequence. And we have 4 families for CA7 singularities: 7.1, 7.2, 7.3, and 4. And these expected moduli space dimensions 35 and 34, and 42. And the second part of the statement is that in each family, except for 7.4, a very general member in a specific sense is terminal and Q factorial. Is terminal and Q factorial. And the proof idea for this is proposition let X be a terminal Gorenstein threefold. D is a smooth, effective anticanonical divisor. Smooth, effective anticanonical divisor. Divisor such that X is smooth along D. And the Picard number of D is 1. Then X is factorial. How do we use this? That I describe the family of centric double solids, and I describe a parameter space of this this D, and I'll show that for these families we have that this D is a very general K3 surface in a suitable parameter space, and very general K3 surfaces have exactly Picard number 1. But this is only for Gorenstein varieties, and one question or future problem to solve is how do we prove factoriality for one of these families that are not Gorenstein? But this is something I'm not sure how to solve. And as the last thing to mention, I'll say what if we only care about smooth varieties? So this solidity that if x1 up to xm are Q factorial terminal Fano threefolds with Picard number 1, such that every divisorial contraction phi one of the following codes. Either phi is not a maximal extraction or phi initiates a Sarkisian, which is a certain kind of birational map. then x1 up to xm are the only Mori fiber spaces in the birational class of each xi. Are the only Mori fiber spaces in the birational class of each xi. So these are all birational. In particular, each xi is non-rational. So, and here's the point where even if you care about only smooth varieties, if xi is smooth, it can be birational to a singular Mori fiber space. But these techniques allow you to prove the non-rationality of the varieties in this case. Okay, that is all. Thank you.
Any questions or comments?
So you talked about CAK singularities on threefolds or sexy double solids. So what about CJK or CK?
Yeah, so that's a good question. One reason why I focused on CAK, there's a known classification of divisorial contractions for CAK singularities. That the classification of three-dimensional divisorial contractions, so these are the morphisms that contract a prime divisor to a point and are in the terminal category. That this classification is almost finished, but the cases that are not done is CDK and CEK with discrepancy 1. That this is something I'm also currently working on to finish this classification, and then possibly, and if that classification is finished, then we can get local inequality for that case also. But this is also work in progress.
And the second question, maybe I was late a bit at the beginning. So, so you told about sextic double solid. What about quartic double solid or double solid?
So these.
So it's not prime. They're not prime, yeah.
Yes, they're not prime. So there, I'm not sure about this birational rigidity notions or rationality notions for them. But what I say about factoriality, these statements actually would prove more generally for double solids. So, in particular, also for quartic double solids. Yeah, we have something like yeah, if there are only a certain amount of points that are singularities of types A1 and A2 on a double solid, then it's factorial. And also something like if there are only, so for sextic double solids, if there are only at most 4 singularities, CA1 singularities of type at most A4, at worst A4, then these are a factorial. But we have such kind of factoriality results for double solids in general.
So you have these circular links. Corti had a paper on circular links for Mori fiber at Clavillados. The circular links are the class of volume preserving birational maps of the chloride in that case. Can you say something about Clavillard, or is it?
I'm not sure about Clavillard. So let's see. Yeah, these circular links in general. Yeah, you don't have to look at Fanos. You can look at arbitrary Mori fiber spaces, and yes, you have this also volume preserving Sarkisian program to get these Sarkisian links. So yes, it goes in more generality. One thing I've been working on is to get this algorithmic that the most complicated part of this whole story is computing the Sarkisov links. That right now in Saarland University, they are computer algebra experts there. They have a computer algebra system called OSCAR that I'm using and also developing. So I'll say OSCAR, a free software computer algebra system. They also got the 7 million grant a few weeks ago, so good system to use. And yeah, I'm using this to make this algorithmic Sarkisov link computations.
Okay, let's thank FAA.
Yes, so what is the definition of this fixed point? So the Hamiltonian which uses this come with a slope. It's not r squared, it's a times r. A is the slope. So that makes the orbit, twist the orbit in the compact set. I guess it's so maybe next time I have to have a flight, so maybe I'll send an email. Okay, fine.
All right. I'm very happy to introduce Rodolfo Aguilar from Miami, when you see the top. Today we talk about the Calabial versus not the Calabial, right?
Yeah.
Calabial versus non-Calabial trifles.
Thank you. Thanks for the invitation. It's always a pleasure to be back in Sofia. So let me mention the structural for the talks. I will give some motivation. We'll recall some classical results on Calabi-Yau triples. And then I will give some recent results with its agreement, this log Calabi-Yau triples. So basically I will speak in three parts. So I will talk about Agile Jacobi maps, Yukawa cubics, and the formation of pairs of the Calabi-Yau and lines on it. So let me give you a very short motivation. Let's consider a generic Calabi-Yau trifold. So I won't give any details here. This is just to have a rough idea. So if we consider the Gromov-Witten invariance, this is going to give a virtual count of the rational, I'm taking 0 here, curves. Let's say of class D in this H2. So we want basically to do some Hodge theoretic study of these triples. maybe inspired by some properties of this. So the main tool that we are going to use is the so-called Abel-Jacobi map. I will define it in a moment. And so the idea is that with these invariants, you only count the number of the curves. So in some sense, they are indistinguishable. So the Abel-Jacobi map will give you the position of these curves on X. So in a certain way, it carries more information. And we have the following conjecture. So this Abel-Jacobi map of the genetic threefold. This is one-to-one on the set of curves of the form C prime and 0 prime. So let's take C to be a rational curve of, and also C prime of the same degree. So the conjecture is that Abel-Jacobi is going to be one-to-one in this set of curves. So this is going to be our motivation. So let me now start with the Calabi-Yau threefolds. And to define Abel-Jacobi, let me just consider for the moment a smooth projective threefold. So we have the following definition: the intermediate Jacobian. Let me denote it by J of X. This is going to be defined as the H3 cohomology of X, quotient by F2 of the second piece of the Hodge filtration. We need to quotient by the lattice. So another way of writing this is the following. So we have the Hodge decomposition of this threefold, and we will be interested in the H12 part plus the H03 part. We take the dual of this, will be quotient by the third homology group. So basically, we want to associate a complex torus to the variety, and we want to study the geometry in this complex torus and see how much this complex torus remembered. And so in this case of the curves on the Calabi-Yau threefold. So now,
excuse me, but could you say a little more about Kontsevich? So you mean Abel-Jacobi map is one-to-one of the set of?
I will define. So you mean the definition of this or about the conjecture?
I mean conjecture. Yeah. So on which curve this is one?
So this curve, so you take a rational curve of the same degree. So you want them to be homologous to 0, and then you can apply the Abel-Jacobi map of them, right? So so the conjecture is that this Abel-Jacobi map distinguish this pair of curves. Is that clear or not?
I see, but C and C prime and C double prime are certain rational curves, right?
Yeah. So C prime, C double prime, this is rational curve of degree. I mean, in the same class.
I see.
Okay?
Thank you.
Any other question? So now let me consider the codimensions, two cycles that I will denote like these, that are homologous to 0. These are the codimension cycles are homologous to 0. And then I can define this Abel-Jacobi map. So Abel-Jacobi map is going to be a map from this codimension to cycles There are modulus to 0 to this intermediate Jacobian, and to every cycle, I'm going to associate a linear function here that is going to be integration on gamma, where gamma has as a boundary this cycle that is homologous to 0. So this is going to be the ideal Jacobian map. So basically you have, we are going to integrate these forms on this gamma. It will give you a map like this. So also, we are going to be interested in the differential of this map. So the differential is given by the following formula, differential of Abel-Jacobi. So we will have a map from H0, and then we need to take the normal bundle of a curve. So this time I'm going to take C, a curve, and let's say a smooth curve on X. We need to tensor with H1 of omega 2 of X. This is going to be to C that I'm seeing at H1 of. So this is basically contractions. I have a 2 form. I have a normal vector, so I'm contracting in the normal direction of the curve, and I'm going to get a one form of the curve, and this is basically C. Or equivalently, I will also see this map as a map going from H0, the normal bundle of C on X, to H1, 2. So once we have this normal bundle, it's essentially controlling the deformations of the curve C on X, and so we are mapping to this space. Let me give you one example of this Abel-Jacobi, and this connects a little bit with the talk of Felipe yesterday. So let me consider X inside P4 to be a general quintic hypersurface. So we have the following theorem due to limits. So we have that X has only a finite number of lines. Let's say L1 until Ln, and then if we take different lines, if I is different from J, then the Abel-Jacobi morphism in the difference of these two lines is not a torsion point. In this complex torus. So basically you are getting something non-zero, and it's weaker than the original conjecture that I put. So now let me write a bunch of guiding conjectures that Clemens stated a long time ago, and as also Felipe was.
Sorry, can you repeat again how this relates to the conjecture?
So if the conjecture is true, this image should be all different, right?
Okay.
So this is just telling you that this is not going to zero,
right?
Even in torsion. So I'm not saying it is injective even on these smaller sectors. Okay. So let me state the conjectures. So let me write it well, but it's just some extra assumptions. So let X be a smooth projective threefold with a canonical bundle trivial, and I consider a map from P1 to X, and let's say that it is locally immersive. So then the first conjecture is that the infinitesimal Abel-Jacobi map, so the differential of this Abel-Jacobi, is injected. So B, for generic X, then X has only isolated rational curves with the normal bundle O minus 1, O minus 1. And so if we specify more to the quintic threefold, we say in the also Felipe was mentioned here, so the generic quintic threefold admits only a finite number of rational curve. Of each degree. So let me attribute this to Clemens. ICM from 86. So these are all conjecture. And so he was also mentioning that this is known for low degree curves, but it's not known in general. And we also have the conjecture that I started with at the beginning. This I learned from Griffith, so I'm not sure if he is the one that is. So the Abel-Jacobi map is injected in this kind of curves that I wrote at the beginning, C prime minus C double prime with a rational curve of the same degree. And so this has the following implication. So it says that the image of the Abel-Jacobi map on these rational curves so this is non-finitely generated discrete map, discrete group, sorry. And so this is a conjecture, but this is actually a theorem of Clemens and later proved also by Voisin. So if you have a rational curves, even if you have only a finite number of rational curves in each degree, I mean you have a lot of degrees. So you take the whole rational curve of different degrees, and you take the Abel-Jacobi map of this. So then for every degree you're going to obtain a finite number of this, but the image of the whole bunch of it is going to be non-finitely generated. So this is known.
Is this Clem's conjecture for general or for very general quintic?
I have here general.
Okay.
Probably not sure if it's known, if it should be very general. I'm not sure, but in the paper he brought generic. But I mean, it's very old paper, so I'm not sure if.
What do you mean by very general?
So complement to
Finite or
okay.
countable. Right?
Okay.
Yeah, I'm not very sure. We should do very.
I think generic is very general.
Okay.
Generic compared to general.
Okay. Yeah, these words are always kind of. Okay. So if you have more questions, this finishes the part of Hegel Jacobi, then I will start with the Yukawa cubic. So
Just one thing, this D part, this regards any threefold, like Calabi-Yau threefold, or just the quintic?
yeah, I'm not sure. Then you say quintic for safety, but so I mean the problem with this is not. I cannot find it like in a book or something, so this is like very good to tell me, and I'm not sure also. Okay, so the Clemens result is for quintic, but Voisin proved it for general. So so it probably makes sense the conjecture also in general.
Okay.
So this is also known. I'm not writing anything new with the cubics, but I'm going to explain later if I have time that we also have this kind of cubics in the logarithmic setting. So let me remind you of this. So consider a family of Calabi-Yau manifolds, and such that the tangent space of the points are H1. So it's a complete family of deformations. So we have a period map. So this is going from the base of the family to the classifying space. This is called the period domain. And then for every tangent vector in this TPM, we have an action. So this is going to be a subset of a product of Grassmannians. The tangent space of Grassmannians can be seen as homomorphism between a vector space and certain quotient of it. So this will actually induce a homomorphism like this. So this is going to be the derivative of the period map, and it sends the HPQ group by the so-called Griffiths transversality. So you only reduce the first coordinate by 1, and you increase the second. And so if you are in a threefold, you can have, if you take a tangent vector like this, you start at H30. Then you apply a vector, and then you go to H21 of X. Then you apply another vector, and then you go to H1 of 2. Then you apply it again, and then you go to H03. So in this way, you will obtain something as follows. So iterating, we obtain a map from this symmetric product of H1 TX, and this goes to the symmetric of H 0k of x. So this is basically 3, 0. So we go to have a map from here to here just by iterating this. And so this is, so if you are in the Calabi-Yau, you can use the volume form to identify this with S3 of H1 of omega x2. And this is trivial in the Calabi-Yau case, so you are going to see and you are obtaining a cubic out of this family. And so this cubic is called the Yukawa cubic, and it is I'm not sure if I should say conjecturally related to the count of rational curves on the mirror. We also saw it yesterday. And so the last part of this Calabi-Yau absolute case, let's call it, is the formation of curves inside the variety, but when you also deform x. So let me now go to the formations. So consider a curve inside a Calabi-Yau threefold, both of them smooth. Now we have that in this case, H0 of the normal bundle is actually going to be isomorphic to the dual of H1 of NCX. So you have to use adduction here. And now as you have that Kx is trivial, you will have a relation like this. And so the obstruction to deform C with X, so you want to deform X, and you also want that C can follow this deformation, so will be encoded in the following part of a long exact sequence. So you have H0 NCX. This is going to the tangent space of the deformation of the pairs, and this is going to H1 of the tangent space of X. So this is the deformation of the Calabi-Yau manifolds. This can be identified with H21 of X using the volume form. And the important here is that we have a map delta going from this H1TX to H1 of the normal bundle. But I'm telling you here that the dual of the normal bundle, of the H1 of the normal bundle, is actually H0. So if you look at this, H0 NC dual. So I'm sorry for writing here. So I wrote a formula for the differential of the Abel-Jacobi map, and the Abel-Jacobi map take values in the H0 of this normal bundle, and it goes to H1, 2. So this looks like the dual of the Abel-Jacobi, or the differential of the Abel-Jacobi, and the proposition is that this is actually true. So delta is dual to differential of Abel-Jacobi. So what this is telling us is that the differential of the Abel-Jacobi will tell you when you can deform a line inside a Calabi-Yau threefold with the deformation of the Calabi-Yau threefold. So this is going to be the corollary. So let N be an element in this vector space that is the tangent space to the deformation of the universal family of Calabi-Yaus. Then the curves that deform to first order in the direction theta are those that satisfy dAj of theta equals 0 lua. Maybe this is a little bit philosophical, but we like to think of this like when you have the Gromov-Witten invariants there, those are invariants under deformation, so in some sense this is going to be related to the differential of the Abel-Jacobi map, but this is not really so I'm finishing here the part of absolute Calabi-Yau. So I would place, if you have questions, to pause a little bit.
In what sense is delta dual to the differential?
Say that again?
In what sense is delta is dual? It's just home of the...
Yeah. So this is easy. This is easy to show in this absolute case. So you just compute the definition of the obstruction map, and you just compute the definition of the differential of the entropy, and you have a volume form that is going to make a diagram commute. This is the first result that I want to generalize in the log Calabi-Yau setting, and this is not easy in the log Calabi-Yau setting. So log Calabi-Yau. So now we'll consider the following setting. Consider X is going to be a smooth projected Fano threefold. Y is going to be a smooth anti-canonical K3 surface. A smooth anti-canonical divisor. And let me also take Z to be the parameter space of curves of degree D. So now this is with respect to this anti-canonical line bundle. So now we're in the final case. And in the final case, we actually have a lot of curves. So there is some variety parameterizing them all in certain degrees. And I'm also going to take a smooth anti-canonical divisor. So we have the following induced morphism. So whenever you take a curve on X, this is going to intersect Y at some point. And so basically, whenever you take a point in this parameter space, this is going to give you the intersection of these points with this is X, this is Y, this is C. So you obtain a map from Z to Y of D, and note that Y of D is a hyper-Caehler manifold, and we will denote by C the 2 form. So people have studied things like this. So we have the following result of Iliev and Manivel, 2009. So they prove that f of Z is a Lagrangian submanifold. basically telling you that if you pull back these two forms, this is going to be 0 on Z. And so what we could show is that you have two ways to compute the values of these two forms. So you take two tangent vectors on Y and compute it and plug it here, or you can take the Abel-Jacobi map and pair it with the H21. So for this, let me introduce a little bit more notation that I'm just going to use it for completeness of the theorem, but it's not really important. So we have maps that go as follows. So you take the derivative of f. This is going from the tangent space. So this curve, this is basically the normal space, H0, sorry. And this is going to the tangent space of restricted to the intersection of the curve with the K3 surface. And you have also a map beta. This beta is a little bit more complicated to explain. This is actually what is doing the magic. Well, let me just note it like this, but it is actually, it goes to the normal space. So you have the tangent space of the image, and this actually goes to the normal space. So you have y of d, then you have inside z. This map goes inside alpha, and you have also some normal vector that is going from this. So the theorem is now as follows. So if you take C on the tangent space of the parameter space of the curves, and you take theta here, then, as I was saying, you have two ways of computing this. So you can just plug in the values, or you have the differential of the Abel-Jacobi map, and you pair it with this theta. So this pairing here on the right is given by pairing H2 of omega 1 with H1 of omega 2 to C. So this is basically the duality of H21 and H12. And so out of this we are going to obtain a similar result of that one, that the differential of the Abel-Jacobi map was giving you the information on which directions you could deform a curve and the variety x at the same time. But now we have to consider not only the formations of the funnel, we have to consider the formations of the pair of the funnel and the Calabi-Yau, but we are going to fix the Calabi-Yau. So consider the universal family.
So can I ask a question?
Yeah, you can ask a question.
Why?
Say that again.
What is the d on top of the y?
That's the degree of the curve. So this is the degree of minus k of x restricted to c.
What does y d mean?
So if you look at the smooth of the points where this is transverse. So this basically means that you are taking d times y and making the quotient by the symmetric degree. You have to do something in the tangential points, but this basically means for the Hilbert scheme of points, the as you prefer. More questions? Okay, so let's consider the family, the universal family. I'm using similar notations of the formations of X keeping Y fixed. And so the tangent space to this family, now this is going to be also as in the absolute case, this is going to be an open of the tangent space of H1 of Tx, but those vector fields that do not move Y, and using, in this case, the log volume form, this is going to be isomorphic to H1 of omega x2. So this is basically the same formula that we had in the Calabi-Yau. And now we have an exact sequence that is basically the same as we had before. Then you write it in the following way. So you have the normal bundle of C inside X, then you have the normal bundle of C inside this big family of universal deformation, and you also have the normal bundle of X now inside this universal family of. And so once again, we take the long exact sequence associated to this, and we obtain a map that we are going to denote by delta, and I guess you can anticipate the result that is very similar from the one that we had before in the absolute case, but there is a small difference. So before in the Calabi-Yau, this H1 was the dual was isomorphic to the dual of H0 of the normal bundle. But in this case, the Kx is non-trivial. So we are going to have only a part that is contributing to so that you cannot deform to first order, and you will have to tensor by Kx. And so this is only a part of MC of X.
So in the absolute case, the base is a ball because of the diameter of here.
But you have Kuranishi.
You have unobstructedness?
Yeah.
Do you have that too?
Yeah. I think so. Yeah. I mean, you have it in the final case because it's unobstructed. You use vanishing theorems. Yeah, but I think so.
I mean, isn't that what it means to say that B is an open?
Say that again?
I mean, you're saying B is an open ball inside this. That means the formal completion at 0 is formal policy.
Yeah.
So that implies that it's unobstructed, or?
I
mean, are you using
in general or in this case?
I mean, using that it's an unobstructed ball.
I think it's unobstructed, the formation of log Calabi-Yau, just as in the Calabi-Yau setting. So the corollary of this is that we have an analogous statement. So the pair Cx deforms freely to first order in the direction C. This is going to be the tangent space to the. Whatever it is of this family. So if and only if the dual of the Jacobi map at this tangent direction is 0. So this is the analogous statement of the Calabi-Yau setting. So let me quickly define the cubic in this logarithmic case. Now, so now, let me go to the cubic. So this time, we need to fix an equation of the log Calabi-Yau surface, and I will see this anti-canonical bundle for these sections as H0 of X wedged to the tangent space to the 3, and this gives the following. So if you consider a section here, you can use contract also the two forms, and this is going to give you an H1 of Tx used by using this. And now the period map, or rather the derivative of the period map for the final threefold. So we obtain a map from H1 of Tx, and this is going to the homomorphisms of H21 of X, and we have Griffith's transversality again, so this is going to decrease this by 1. And so you can basically write this as S2 of H21 of X dual. And so we just have to compose these two. So we applied something like this, and now that we are in H1 of Tx, you apply the derivative of the period, and so together we have a map as follows. So from H0 minus K of X, so in this map you just dualize this H21, and this is going to go to S2 of H1 of omega X2 dual times H21 of X dual, and this is going to S3 of H1 omega X2 dual. So this cubic has appeared before in work of Kontsevich. So they are interested in integral system. We could show that for the generic cubic threefold, this cubic is smooth. So let X inside 4 be a generic cubic threefold, and also the Y should be generic minus K of X generic. So then the cubic CY is smooth, but we have examples. For example, if you consider XY the Fermat pair, meaning that this is the Fermat cubic threefold, and this is the given by a section with Fermat equation. So then this cubic is 0. So I'm not sure if people have considered this kind of Yukawa cubics in the local Abiyao setting. I'm not sure if they kind of count rational curves that are intersecting the Calabi-Yau surface in certain ways, so they probably should intersect this with some fixed point, but we are not really sure. We have the example of the cubic threefold, the quartic threefold, and we can count the most basic type of curves, lines, or basically lines, but we don't know if this is known, if there is literature around this. But we have a lot of questions around this. We can ask the Clemens questions in this setting, and we don't even know how to define the Abel-Jacobi map relative in this setting, taking the curves like this. So I will stop here.
Any other questions or comments?
So how many are there?
How many are what curves? I mean, in the cubic threefold, you are really counting lines.
Oh,
so
yeah, how many lines?
So there is only one, because you have the cubic threefold and the line will intersect. So y is going to be given by two polynomials, the polynomial of the cubic threefold and a polynomial of degree 2. So it's intersecting in 2 points, so 2 points determine the line, and basically you have one. In the quartic, I know there is a finite numbers, I don't know precisely what's the number.
Okay, let's thank you for the moment.
I guess you can go to the toilet 5 minutes, right?
Yes, 5 minutes break. Professor Alexander Schmidt, and today he talk about general coherent systems.
Thank you. Well, so before I will start my talk, I would like to invite you to thank the organizers and their helpers with a big applause for this wonderful event. So my talk will be one of the talks which are only loosely related to the main topics of this conference. I would like to present a moduli problem for vector bundles on curves. I will say something about the notion of semi-stability and the existence of moduli spaces. So I will work over the complex numbers, and X will be a connected smooth projective curve. Of course, the complex numbers. So I will spend a lot of time on introduction and background. So the very classical situation is that we have a morphism from the curve to a projective space. A morphism with non-degenerate image. So it should not land in some hyperplane. So then we can pull back the tautological bundle on PR to X, and we get a line bundle, and I will denote by D its degree. And we get a subspace of the global sections of L. And if I assume that the image is non-degenerate, then this will be a space of dimension R+1. So these data determine phi up to the shortest coordinates, and this is what is classically called base point free I just remind you of some classical problems. So if you fix a curve, you can ask for which R and D does there exist a base point free X, or another famous classical question, which is discussed in Hartmann's book, for which GDR does there exist a smooth curve of genus G and degree D in PR. And of course, especially the first question is leads to the Noether theory, and this we will find in the famous book of Alvarello, Cordanda, Griffith, and Harris. And what I would like to point out here is that from our modern techniques, it is easy to construct a parameter space for these triples consisting of a curve, a line bundle, and a linear subspace of fixed dimension in R. So just discrete invariants G, D, and R. So this classification province, the objects we are looking at from a bounded family, they can be parameterized by a scheme of finite type over C. So this was part A of the introduction, and part B is about coherent systems. So we would like to study similar objects, but instead of L, consider a vector bundle. So a Noether pair or coherent system is now a pair which consists of the vector bundle on E and a space, subspace of the space of global sections. So E vector bundle on X and B a linear subspace. And so we get a discrete invariant, so this is so-called type, which consists of the rank of the vector bundle, its degree, and the dimension of V. Okay, so of course it's natural to fix these data, but even if you do, the problem is still unbounded. We have seen this in the talk of Schöne about moduli vector bundles. So for fixed R at least 2, degree and dimension, there is no scheme of finite type over C, which parameterizes all coherent systems of type and S. So modular problem is not bounded. There are too many of these objects. And you can also imagine that you can have very degenerate situations where E is just a direct sum of line bundles, and there might be one with very positive degree, and then you would have a lot of sections, so basically have the classical problem. So in order to get some reasonable problem, one needs a notion of semi-stability, stability, and in this case it depends on a positive rational number, and one defines the slope, alpha slope, of such a pair. Take the degree of E, and we add alpha times the dimension of this space, and we find the rank of E. So if you forget this part, then you just get the classical slope for vector bundles. And then EV is alpha semi-stable if and only subbundles, the slope of F together with the induced subspace is less than or equal to the slope of EB for semi-stable, and for stable, let's take discrete inequality.
So what kind of V are you thinking geometrically?
Sorry?
What kind of subspaces do you can consider geometrical, like coming from geometric problems? Do you have a specific examples of V? I mean, you are thinking very general, I guess.
Well, I mean, I will
okay.
Just make a remark about this a little later.
Okay.
Okay, and then we have the construction of moduli spaces. This is due to Symplectic and independently to King and Newstead. So for fixed stability parameter, you get moduli space of stable things inside the moduli space of semi-stable things. And so the situation is analogous to the case of vector bundles, as Andras has explained. So if you would like to study the classification problem, then you get a nice solution for the stable ones. So they have the isomorphism classes correspond to the points in the moduli space, but this might be only quasi-projective, and you have a nice natural compactification by the semi-stable ones, but then you have to modify the equivalence relation for the ones which are semi-stable but not stable. So it's a similar picture. Okay, and well, now I say something about motivation. So if alpha is small, then you get a morphism from the moduli space of coherent systems to the moduli space of vector bundles. And so you get interesting loci in the moduli space of vector bundles. And this is a famous moduli space, intensely studied, and this gives you nice loci, something like theta divisor, for example. And so this is relevant for the geometry of that space. And this would be also some kind of generalization of the classical picture, just study instead of line bundles, stable vector bundles, for instance, how big can their spaces of sections be. And you have also a geometric situation, so you can look at the evaluation of the sections on E. And if this is generically subjective, then you get a rational map from the curve into the Grassmannian of R-dimensional of V. So these kind of objects arise also in this time, the projective geometry of X. Just looking add morphisms to Grassmanns. Okay, is this enough as motivation? Or, well, the question which you are asking is of course a bit difficult because this is a very huge project, this Bulgaria project, and the status is not so great at the moment. And, so some basic questions. On the geometry of these so-called Bulgaria loci, so emptiness. Dimension, irreducibility, and whatever. Have not been settled in general. And in cases where you have certain situations, under certain conditions on RD and S, you have some more general answers, but then we look quite different from the classical theory. For example, classical theory, you have this Renoir bound, which tells you something about the non-emptiness on a very general curve, and so this is a nice equation. But here this looks more like a zigzag, so you don't have the mass behavior predicted by general considerations. Good, and the last kind of objects which I would like to discuss because we need them are decorated vector bundles. So I fix a finite dimensional C vector space and a representation of GLR C on this vector space, and so if I have a vector bundle of rank R over X, then I get an associated vector bundle E rho on X with typical fiber. And I can now study objects which I will just call O pairs. So this is E comma sigma with E a vector bundle of rank R on X, and sigma a section of E rho tensorized with L, so I also fix a line bundle on X. Good. So if you forget about the L, then such an object describes your amorphism from X to the stack quotient of A by the action of GLR. So in this way they have occurred in relation with Gromov-Witten theory, and that is a recent paper by Fernandez Herrero and Van Leisner, which discusses this kind of objects from this new viewpoint on GIT. And yeah, to give you a famous example, which has been mentioned, if you take the adjoint representation, so in this case, just the action of GLR on R by R matrices through conjugation, and L, the canonical line model. So then sigma is the same as a twisted endomorphism from E to E tensor rise with omega x. So this is what is called a Higgs bundle. Higgs bundle are a famous example of this kind of objects, but many others have been studied in the literature. And there's also a condition of semi-stability, which I will not define fully because I will define something similar in the second part. But we have a notion of semi-stability, which depends again on a positive rational number. And the test objects these are weighted filtrations of E. So which means that we have just a filtration of E by subbundles, so it doesn't have to be a full flag, something between 1 and R, minus 1, and so this is the flag, the filtration, and then we have a tuple of positive rational numbers. So this is somehow similar to classical invariant theory, where you look at one parameter subgroup, say we have the action of SLR. One parameter subgroup gives you such a filtration of the vector space and these rational numbers, which are computed from the weights. And it's an observation which you find in Mumford's book that actual nu just depends on this weighted filtration in the classical case. So these are test objects, and I just need the following expression, which I can form when I have such a weighted filtration. So I take the degree of E times the rank of EI. Wait, it's with alpha, so Good. So this. Okay, and I would like to point out that this induces a weighted filtration of the associated vector bundle E rho. And well, what is in general complicated is that this filtration will be in general longer than the original one. Standard moduli problems like coherent systems and so on, regular pairs and so on, don't see this phenomenon, but when we take, for example, rank 2 and a vector bundle of rank 2, then the only test objects which are interesting are line subbundles. And now if you look at the filtration of, say, the second symmetric power of the dual of E, then schematically you have, so thinking in terms of matrices, you have the subbundle consists of this kind of matrices which correspond in this case of weight 2. Then you get this kind of matrices where you have things of weight -2 and 0, and then you get the whole bundle. And it is induced beta somehow. And so this indicates a bit the complexity of the notion of semi-stability, which I will formulate a bit later for coherent systems in general. And another remark, so this example shows that you can also treat nice geometric objects. So because if you have a homomorphism from the phi sigma intersection of S2 of E dual tensorized with L, which is the same as such a homomorphism, and this gives me a divisor D in the classical projectilization, which is generically a 2-to-1 cover. So if this is not surjective, then you have full P1s as components, but if it is surjective, then you have this kind of 2-to-1 cover inside the projective bundle. And of course, if you take other degrees or higher ranks, you get then hypersurfaces of degree D inside, or families of hypersurfaces. Good. So, and the general coherent systems now combine these two objects. I take a rho L as above, and then a coherent rho system. What looks as before, but is the following. We have again a vector bundle of rank R over X, and V is a subspace of the global sections of E rho tensorized with L. So in the case of the adjoint representation, this let's say we omega x, so we have a subspace vector bundle of the global sections. This vector bundles are linear system of twisted endomorphisms or linear system of Higgs bundles. So these are also called coherent Higgs systems. And they were proposed by Letizia Pamela Paz, Oscar Garcia Trana, and Peter Goten. They wanted to look at these kind of objects to study the geometry, certain aspects of the geometry of the moduli space of Higgs bundles. Good, and now I can explain you.
Is there some, representation theory interpretation?
Sorry?
Is there representation theory interpretation? Pair decorating. And is there a kind of hidden narrational 시샤들이죠?
Sorry?
Is there a kind of narrational 시샤들이죠 for this case?
Kobayashi.
Yes, I will come to that, yeah. Exactly. Semi-stability, so if I have a weighted filtration of E's, as I have pointed out, I get a weighted filtration of 0. So let me just write down filtration, and now I just look at the dimension of the intersection of V with the space of global sections of Fj tensor L. And now I can write down the second part of the stability function I need. So this is define the alternate sum. So I take the weights from this weighted flags, and I take the sum. Okay, so if you know the computation of Mumford's mu on the Grassmannian, then this will look reasonable, and so I call.
Sorry, what is beta?
Sorry?
Beta?
Beta is here from the weights. Ah, right, so beta. Good, and so EV is now delta semi-stable. If for all weighted flags of E, one has that this number m of E dot alpha dot plus delta times this mu is greater or equal to 0 for semi-stable or strictly greater than 0 for stable. So this looks horrible, but you should think as an analog of usual geometric invariant theory. In general, you have the Hilbert-Mumford criterion to check semi-stability, which asks you to check all non-constant one-parameter subgroups. And so all weighted filtrations of your vector space in case of an SLR action. So it is very complicated in general, and only in certain nice cases you can simplify it. Good. So this is the general notion, and this, of course, if the representation is difficult, is difficult to avoid this. If you just take the standard representation of GLR on CR, you get the usual notion of semi-stability for coherent systems, because then the associated flag is the same as the original one, and then you have just a linear combination of terms, and you just have to study the terms one by one, which are these slope conditions. And so the results have been published are the following. So if I take positive numbers R, A, and S, and B in Z, then there exists a projective moduli space and so as to be fixed in delta for all these delta semi-stable in V with in a vector bundle of rank R and degree D on X V is a subspace of the space of sections of A for tensor power of E, and there is a condition on delta which is a bit unpleasant. So if A is 1, then it has to be read as infinity, so there's no condition as in the classical case, and in the other cases we have this restriction. So this is the one thing, and the other thing is what you asked for. My PhD student Cesar Goretti proved Kobayashi Hitching correspondence based on work by Bradlow, Yathia, and Bundet. So they have a very general version of the Kobayashi-Hitching correspondence, and it takes some work to specialize to this case and to find out what the stability condition is that you get, and it turns out to be exactly the same that I wrote down here, so which is a good indication that it is the natural notion of semi-stability one finds. And yeah,
can he explicitly, describe what representation?
Well, it's not. It's not representing correspondence between representations. It's something about connections.
Yeah, that correspondence connection. Is there something?
Explicitly created some equations and solutions of these equations give homomorphic structure on the vector bundle and these data which satisfy this stability condition.
So may I ask a question? So the idea is that you consider these slopes with rational numbers in order to obtain the projectivity of the moduli space. Because if you don't because you could consider slopes not using the rational numbers, right? It's just zero, like for instance in the Simpson correspondence. Because
so what do you suggest? I mean,
so no, I'm just asking. So the reason why you consider these modified slopes is to obtain the moduli space projective space.
Well, I mean, okay, if you look from the, this is something I was going to write down anyway. So if you do a GIT construction for something like this, then you have the what scheme which parameterizes the vector bundle part, and then you have something which takes care of the other part of the linear series. And well, you want to do GIT on this space, and you have to pick a line bundle, an ample line bundle for doing that. And you know the line bundles on the quad scheme, and so this gives the first part of the formula. If you have a general one parameter subgroup of SLW, then this is the kind of weight you get. Good, and so this is also the linearized line bundles on this quad scheme. They correspond, because the stack of vector bundles is smooth, they correspond just to line bundles on the stack of vector bundles. So you know these line bundles, so you know there's basically just one point for this. And here you have the natural line bundle from a tautological quotient. And so the only parameter you have is, so you put something like OAB, and this ratio EB is somehow related to this delta. And yeah, of course, this comes in a very different form, and the problem is to make it intrinsic, but yeah, some experience. And so this condition I wrote here actually guarantees that I pick an ample line bundle, because the problem here is in this computation, so technical problem, technical difficulty, which makes this proof a bit more involved than previous computations. So this is, here you can construct a parameter space, a group action, but if you have a positive thing, then this, in this kind of portions, you consider you get an identification. So this is the space of global sections of E twisted by n to the power a, and of course this is not the same as the thing you really need, which would be so this makes it difficult to adjust the linearization, and since you want an ample linearization to get projective moduli spaces, and so that you can actually do computations with the Hilbert-Mumford criterion, you need this condition. Good, and so we still don't have an idea what it means. I mean, there's also another approach which uses the fact that you can just take the usual decorated principal bundles for this space, for this S called direct sum of the representation E rho, and then you look at the construction for the decorated vector bundle case, and look also at the action of GLS. So then you take another quotient, you get another notion of semi-stability, which is even a bit more complicated to state. But there should be a way to transform the parameters, and then this approaching, delta approaching this bound in this picture would mean the parameter going to infinity in this other construction, which seems more reasonable. And so to give you a final idea how this could look like, this is kind of potential example because it means that we have some notion of asymptotic semi-stability. Well, so if you approach the threshold there, then this example should be asymptotically semi-stable. If there are two conditions, there is no subline bundle and in E, which is isotropic, for all beta and B, and agrees with the radical of 1 beta Lorentz linear series. So there should be U9 one with these strange properties. And the other condition is for any line subbundle which satisfies 1. E, which is isotropic for all beta in B or agrees with the radical of 1 beta. In this linear series you have some kind of condition, and then this. So there's no more parameter because study some asymptotic. So this should not violate the vector bundle semi-stability. And so you arrive at this kind of condition if you just study the classical GIT problem. So you just have a two-dimensional vector space of two copies of the vector space of symmetric matrices, and look at the action of SL2, 2x2 matrices in this case, and just look at the action of SL2 and compute semi-stability. You find such strange conditions, and this should translate to this kind of asymptotic condition. Okay, I stop here. Thank you very
much. Okay, any other questions or comments? If not, let's thank the speaker. Okay. I guess there is downstairs some refreshments. Right.